All right, up in the booth, can we get the live stream started? Okay. That one line didn't go down.
It never goes down.
Oh, okay. All right, looks like we're online. Welcome, everybody. So for the past 10 weeks, these students have been slaving away at their research projects. So it's really hard to kind of get novel research results out in 10 weeks, but every year we find a way to do it. So today, they're actually going to present the fruits of their research. So we're going to have 8 talks, one for each student. So approximately 25 minutes for each. So we'll have 7 minutes of question and answer for every student, so come prepared. We have refreshments in the back, so please eat them. We have so many of them. And for those online, so we have the live stream going. And in the comments, you can leave your questions. I will be monitoring it. So note that there is a little bit of a lag. So I may not get to your question immediately. So try to post it early so I can get to it later in the Q&A session. First off, so we have Aileen Niesta, so from the University of Verne. So, and she is going to be talking about predicting what the solar wind using Parker Solar Probe. So, and we'll get her started here in just a few seconds. Okay. Can you just give a little test into your loud mic?
Testing.
Yeah, a little bit higher.
Testing.
There we go. Let's just wait just a second.
Chad's waiting for the second hand to take up the authority.
Anticipation.
We're like Swiss trains here. All right. All right. Aileen, please take it away.
Okay, my name is Aileen Niesta. I'm from the University of Verne, and this summer I worked with Dr. Sam, Dr. Mike, and Lydia, and my amazing co-authors on can we predict the solar wind at Earth using Parker Solar Probe measurements. So what is the solar wind? So the solar wind is a continuous outflow of charged particles that mainly consist of protons and electrons, and they're emitted from the sun all the time. And this stream of particles shapes and interacts with planetary magnetospheres, most importantly Earth's. And that's what causes what we call space weather. And typical speeds of this solar wind is from 400 to 800 kilometers per second, but that can vary significantly. So why is predicting space weather important? So even though the solar wind interaction with Earth's magnetic field causes these beautiful aurora lights, they can also cause satellite disruptions, harm to spacecraft and astronauts, and affect power grids and GPS navigation. And those really strong events are what we call geomagnetic storms. Therefore, predictions of these events are crucial for mission planning and as well as safeguarding the systems that we have on Earth as well as on the ground. And this project focuses on predicting the background steady state solar wind instead of transient events like coronal mass ejections, so not these big explosive events. So the solar wind is currently predicted usually using one of 2 approaches. So the first approach is to use forecasts from satellites at the L1 Lagrange point, and that's where this little point is. It's about 1 million miles away from Earth, and that's where we have these satellites hanging out. So these are real measurements taken closer to Earth. The other approach is to use large-scale magnetohydrodynamic models, also known as MHD models, and these simulate the inner heliosphere as well as the corona, so it simulates where the solar wind originates from, and it also projects it out to 1 AU, so where we're able to predict it. And even though these models can provide a decent lead time, their accuracy is limited due to the fact that it's simulated. And yeah. So now we have Parker Solar Probe. So Parker now gives us direct in situ measurements of this potentially earthbound wind, so where it originates from. And it can give us several days of lead time. So this is kind of a scale of what we're working with here. So this is the sun, this is where Parker is usually. So very, very close. And on the complete other end, we have Earth and where those L1 satellites are. So very large difference between those. So we're hoping with now having these true physical measurements of near sun conditions, not the modeled kind, we're hoping that will lead to more accurate predictions. And just to note, we're using data from Parker's closest approach from encounters 1 to 23. And this is a picture of Parker Solar Probe. So how are we going to take these velocity points and project them out to 1 AU? We're going to be using HUXT, which stands for Heliospheric Upwind Extrapolation with Time Dependence Model. And this is an open source Python tool that propagates the solar wind using a simplified version of a very complicated MHD momentum equation called Berger's equation. So what HUXT does is it takes that equation and assumes no external forces. So it ignores gravitational forces, thermal pressure, and it's also much faster than most MHD models can run. And all you need is an input solar wind velocity at 30 solar radii. So this is like the full boundary, or basically where we're projecting it from. So it needs a 360-degree boundary from around there. And what it does is it propagates that solar wind out, and this is where Earth is. So it projects it out to where wind and those L1 satellites measure their data from. So our hypothesis is, can we use Parker's near-sun measurements, propagate them with HUXT, and get better predictions at Earth? So this is the pipeline that we have so far. So first, we start off with these in situ measurements from its radial velocity data from SWEEP. Then we make these combined boundary conditions that I'll get into in the next slide, and put them into HUXT, and then we get an output predicted velocity time series at 1 AU. And this is where we're comparing our predictions with real L1 data. So the first part of data preparation is to download all the Parker velocity data from all 23 encounters. And instead of extracting all the measurements from the entire Parker orbit, we're just extracting the prograde portion of each orbit. So that's this little red section of data here. So not only is it when Parker gets closest to the sun, it's also when Parker moves in respect to the sun's rotation. And then what it's doing, this is our measurement time here. And then what it does is it projects that solar wind out, and then that's where Earth is. So if it's on this side, it'll project it to where Earth is here. Another thing we have to deal with is that, so our standard HUXT input is 30 solar radii. So it's that far away from the sun. But when Parker measures the velocity data a lot closer than 30 solar radii, we have to deal with residual acceleration. So some of these points that get as close as 9 solar radii haven't fully accelerated to their steady state velocity. So once we accelerate them, we got all these data points at what they would be at 30 solar radii. So now we're ready to input them into HUXT. So as I mentioned before, to run HUXT, we need a full 360-degree velocity boundary at 30 solar radii. So this circle here, you can see where we have our Parker data. So that's just a portion of that 360-degree boundary. And then we're going to be using MASS, which stands for magnetohydrodynamics around a sphere. So that's one of those simulated solar wind models, as I mentioned earlier. And so we use half Parker data, or a fourth of Parker data, and the rest is simulated data. So now we have a full boundary that's ready to be put into HUXT. So at the end of combining those conditions, now we have 3 data frames to work with. We have just using MASS, which is the simulated data. We have MASS plus Parker before the residual acceleration correction, so just Parker's raw data. And then we have MASS and Parker after the residual acceleration correction. So this is just looking at what we get as the output. So this is a time series at L1. So the magenta line is Parker plus MASS, the corrected version. So you can kind of see this magenta line here. The blue is what's actually measured at L1, and the black dashed model is just the simulated data. So you can see here, this is our time of Parker measurement, so that little portion. Then we have the Parker scoring region, as well as the Parker prediction region. And the yellow shading is when a coronal mass ejection was observed at L1. So for scoring our predictions, we're going to be using the root mean squared error, also known as the average difference between prediction and what's actually measured at L1. So a lower RMSE value means a better match or a better prediction. And we're calculating RMSE in the region only where Parker's influence reaches Earth, so in that little gray shaded region from the previous slide. And we're comparing all of these 3 data profiles to what's actually measured. So we end up with 3 RMSE scores per each encounter. And this black line here is our baseline. So we're trying to see if our Parker data with mass is going to outperform the baseline model, so just simulated data. So just by looking at this, you can see that there's regions where RMSE is a lot lower for all the models and even for our model here. So you can see where it's better, worse, and no change. But towards the end of the later encounters, we could see that our prediction almost always outperforms mass alone. So you can kind of see that there. So now going into the slides that I pointed out with the red arrows in the previous slide. So for encounter 7, we have an example where the Parker corrected profile clearly tracks the solar wind features better than mass. And the RMSE score reflects that improvement. For encounter 10, even though the RMSE is worse for our accelerated profile, visually it still captures that major rise better than mass. So that's the limitation of RMSE, because even though our model is catching these peaks a lot better, RMSE basically calculates it by subtracting these 2 peaks here. So that's the limitation that we have, because it's not actually looking at the overall shape, it's just looking at the values themselves. And then for encounter 14, we can see that sometimes all the models struggle. And we're assuming that because there was a coronal mass ejection present here, that could have caused all the models to struggle in that instance. So now we can look at the distribution of the root mean squared error scores. So just by looking at this, we could see that our magenta line, which is our accelerated model, is shifted further left, meaning that they have a consistently lower RMSE value, and mass values are skewed higher, which means they produce larger errors, and they're shifted a little more right here. And then looking at this line here for our non-accelerated profile, we can see that doing that residual acceleration correction did indeed benefit our predictions. So now we can look at different encounter by encounter trends. So looking at this blue line here, we can see that Parker gets a lot closer to the sun throughout its encounters. So this is measuring versus time here for both axes, or for the x-axis. So this is going along from encounter 1 all the way to encounter 23. And we can see that it gets much, much closer. It actually gets up to 9.86 solar radii. So that distance from the sun affects how early we can observe the wind. You can see that there. We also can note that solar activity increases over time. So when we hit solar maximum around here, you can see this line increase. You can see that there's a lot more coronal mass ejections present, which are those gray lines here. Okay. So now we can look at latitudinal and longitudinal comparison. So we can see here that in encounter 1, this latitudinal comparison has a very high RMSE value. And that can be because they're further in latitude. And then in encounter 7, we can see that we have a very low RMSE value. And you can see that they're a lot closer in latitudinal comparison. So what latitudinal comparison means is that this plot tracks how far Parker was above or below the solar equator compared to Earth. So if they're in the same plane, pretty much. And we could see that there is a correlation here. And then for longitudinal comparison, that's measured as the angular separation around the sun. So we can see here there is no very strong correlation, or at least as obvious as the latitudinal comparison is. The angles are about negative 208 and negative 44.9, and these don't necessarily correlate as strongly. And then this is kind of looking at them plotted against, or just looking at them plotted in a different way. So we can see here that for the latitude, RMSE value tends to be a lot lower when Parker is close to Earth, as we mentioned in the slide previously, suggesting that this is definitely a factor that affects our prediction accuracy. And then we can see in this plot here that even though we do get a lower RMSE value occasionally, the correlation isn't as strong. So far we've developed a pipeline to incorporate the Parker Solar Probe data into HUC simulations instead of relying solely on just the simulated model data. And so far we can say that predictions using Parker data generally outperform mass alone, which is a really good sign. And our best results occur when Parker is closer in latitude, and Geometry, distance, and solar activity may all play a role in prediction accuracy, and that's something we're going to be looking into. And we also note there's a variability in performance, especially during when coronal mass ejections are present or when there's complex solar wind conditions. So therefore, we're actively investigating how these factors interact and where the Parker advantage is clearly the strongest. So for future work, we have 3 main goals. So one of them is to address the limitations of RMSE value by implementing another alternative scoring metrics. So like I said, if we remember the other plot, it wasn't clearly capturing the overall structure, so that's something we're going to be looking into. Also conducting a detailed analysis of the orbital geometry, so looking further into latitude and longitudinal alignment, and also seeing if the solar cycle phase has any dependencies. And also expanding our analysis, instead of just looking at the prograde range of the orbit, looking at the full encounter data. And luckily, this investigation is being extended beyond the summer in collaboration with our team. And yeah, thank you, Sam, Lydia, and Mike for being great mentors. Thank you, Chad and Kathy, for running the program and admitting me. And thank you, NSF. So, yeah.
All right. And thank you, Aileen, for finishing early. So, and your reward for that is more questions. So, we're opening up the sorry, accidentally flick that off. So, all right, we're opening the field to questions. So, if you're online, just put them in the live chat, and I will read them. All right, Torsren.
Thank you, Aileen. Back where you were comparing how well the different models did by their RMSE, you had a couple of Gaussians, or I guess distributions. Yeah, that one. How certain are you statistically that those aren't the same 2 distributions? Have you done, I think it's like, my statistics is kind of bad, but like the student t-test, I think?
No, so this is looking at basically the density of where the scores lie, pretty much. Mm-hmm. So you could see that because our magenta line here, our accelerated version, is shifted left, that means that most of the scores lie within this range. Yeah, so it's a very small difference, but definitely, at least a little better than the black line, which is what we wanted to see.
Awesome, thank you.
Yeah, of course.
All right. Jonathan.
So your input data, of course, is like maybe 30 to 40% Parker and 60 to 70% the mass model, because we don't have 3 Parkers showing all the way around the sun, which would be nice. To what extent do you think that's limiting this? In other words, do you think it makes a big difference that we only have that little arc of Parker data to improve things?
I would say that's definitely one of the main things that I would like to focus on next, because we do have an idea of what the solar wind is like very, very close to the sun, which is why we're just using prograde data. But it would be interesting to see how it evolves over time and what the Parker measurements look like as it gets further away from the sun. So I think that's definitely something that can affect our predictions.
More questions? Amy.
So you mentioned that there could be other metrics that you may be using in the future to try to quantify how better Parker's doing. I wonder if you had any ideas of what those could be.
Yeah, so actually Lydia and Sam brought up one. I forget exactly the name, but it's something that basically quantifies using the overall shape of the peaks. So we do have a lot of instances, like in Encounter 10, where our profile is catching this peak a lot better than masses. Mass is all the way down here. So I'm not exactly sure what it's called, but that's what the metric does pretty much. So it looks at the overall shape of things, even if they're a little lagged. Yeah, because that's a problem with. Yeah, exactly.
Still have time for plenty more questions. Kathy has a question.
This is sort of a follow-on to Jonathan's question about, using the Parker data for part of the boundary and the mass data for another part of the boundary. At any point, did you sort of plot the solar wind speed kind of along that boundary with the Parker data and then the mass data, and to see if there are any like discontinuities. Were there any places where it was like obviously not matching up or anything like that?
Yeah, actually, so there is a lot of instances where the mass data is a lot smoother. So I actually don't have a plot on that right now, but there was a lot of instances where, say, where the cutoff was, where we're using mass and then we implement Parker, there was like a very steep drop. So that's definitely something to, I guess, look into and correct for the next time. But yeah, there was a lot of instances where it wasn't exactly the smoothest transition. Yeah.
And did you do anything to smooth that out, or did you just kind of live with it?
Kind of live with it, yeah. Yeah, but when we did do the residual acceleration correction, it did make it a little better for some instances, but there was some times where, mass would predict a very strong or very fast speed of solar wind when what was actually measured it was lower or something. So. Yeah.
Any more questions? We have so much more time to grill her. Come on. Bail me out here. All right. Matt.
Thank you for a very clear and interesting talk. I had a question about the Parker Solar Probe data. You showed a trend early on in your talk that indicated the quality of the data or the quality of the encounters might be diminishing over time. And so I wondered if that would have an impact on your future analysis, if you were planning to incorporate those data and how that might affect your plans.
Yeah, so in the early encounters, we had a very, small prediction period. So I'm not sure if any of these show it. So actually, you can see here. So if we look at early encounters, so this is encounter 7, so this isn't really like the very, very early encounters, but you could see that this prediction range is shorter than, say, something from a later encounter, and that does proceed to grow over time when we get into the later encounters. So we would get more of a prediction time as we look in the later encounters when Parker is a lot closer to the sun. So, so out of, I guess, all the encounters, it would be more interesting to look at the later encounters. They do give us more of a lead time because they're a lot closer in distance. So.
Torsren has another question.
What's the mass model based off of, actually?
So that's a simulated MHD model. So
that's from like looking at the sun as just like looking at like the, I don't know, like imagery from that and making a model based on that.
Yeah, so what the MHD models are is very, it uses like real equations and real physics and basically does this giant simulation of what they believe the inner corona and the corona and the inner heliosphere look like. So it does use real physics, very computationally demanding for the most part, but it's not real measurements, if that makes sense, yeah.
It usually uses the magnetic field as the boundary at the sun.
Yeah.
All right, we have time for like one really hard question.
Please no.
Oh, let's go with Tilly.
This is not a hard question.
Okay.
What was the most rewarding part of your work?
I would say seeing, let's see. So I actually came up with this yesterday because Yami had a brilliant idea to compare distribution scores. And we did have basically, it was pretty obvious to us that our modified version was outperforming mass, which is like the simulated data. But actually seeing it in this way to where it was, I guess, more obvious than looking at those time series plots, I would say that was like one of the most rewarding things because it showed that it actually does better than, it beats the benchmark. So, yeah. Thank you.
one more question, maybe not as hard as requested last time.
Maybe just like to go back to Jonathan and Matt's questions. You just had the plot where we have the boundary condition all the way around the sun,
Yeah.
and a chunk of it filled in by Parker. Could you just explain how that changes with the mission, like at the start versus near the end?
Yeah. Let's see. Okay, so in the beginning, actually. Okay, so we can look
And
at this one.
how does
and
it
then-
how does it relate to like how long a period of time you can predict at Earth?
Yeah.
Yeah.
So in the early encounters, this little sliver of basically the Parker data that we're taking is a lot smaller. So I wish I had a plot that showed the early encounters, but it's very, very small. So this is one of the later encounters, and this is a very wide region as compared to the early encounters. So as we get later and later, we get more of this gap filled. Yeah, so that range of measurement becomes a lot longer. So that does give us, I guess, a larger amount of prediction as compared to the early encounters. We had a little bit of measurement and a little bit of prediction. So yeah, that's how it evolves over. Thank you.
All right, let's give one more round of applause for Aileen. All right, please stand by while we swap over to the next speaker.
Bring it on. Hello? Is this better?
All right. So just a reminder to everybody online, so even though it says comments are disabled, the live chat is active, and that's where you should actually place your questions. All right. So for the first time in program history, we have accepted siblings into the program. So we have a large contingent of the Brent family here from North Carolina. So, all right, first is the elder sister, so Sitara. So Sitara Brent is coming from Appalachian State University. So, and she's going to be talking about how to predict geomagnetic storms using both instrumental data as well as some modeling. So, whenever you're ready, take it away, Sitara.
Hi everybody, I'm Sitara Brent, and I'm following a filament eruption from the sun to the earth that caused an intense geomagnetic storm. I did data analysis and modeling, and I worked with Dr. Nishu, Dr. Tatiana, Mr. Lucas, and the Solar Wind team. So this eruption took place 2024, October 8th, and as you see, that is the filament that led to the intense geomagnetic storm. A geomagnetic storm is a temporary disturbance in the Earth's magnetic field. This filaments have magnetic field, coherent magnetic field structure, and high density. When an intense geomagnetic storm hits that has an opposite magnetic field and fast speeds, understanding the connection between filaments, coronal mass ejections, and intense geomagnetic storms is vital to make better models to help us better predict the time it will take a CME to interact with the Earth. The pathway that we'll be looking at during this presentation, first we'll be out on the sun looking at the filament using AA and SDO, and then we'll go into interplanetary space looking at our coronal mass ejection and our interplanetary coronal mass ejection using SOHO and Stereo A. Lastly, we'll go to Earth looking at our intense geomagnetic storm using OMNI data. So in the first video here, this is basically kind of what the filament looks like as it's leaving the sun, so the so the sun's magnetic fields can reconnect. And then in the other video here, as I said, those are opposite magnetic fields, and that compresses the Earth's magnetic field, causing a violent disconnection. Following that, solar wind and then reconnecting at the end. So these, for our coronal mass ejection observations, we'll be using spacecraft and databases. So first we have our SDO, which will be looking at AAA 171, 193, and 304 in extreme ultraviolet. And we'll be looking at the filament erupting from 0 to 1.3 solar radii. We'll be paying attention to the density, although you can also see the temperature using SDO. Then we'll be looking at SOHO and Stereo A using C2 Core 2 in white light, and we'll be looking at the CME expanding from 3 to 15 solar radii. Here we'll also be paying attention to the density, and however you can also see flow speed. Lastly, we'll be looking at the Omni data, which is wind, discover, ACE, in time series, which gives us the flow speed, density, magnetic field magnitude and components. And lastly, we'll be looking at the CMH, which is also an Omni using the World Data Center from Cairo. So thinking about our spacecraft location, if you see here in the middle, right here is the sun. Looking at where Earth is, dot number 2, that will be where our SDO, SOHO, wind, ACE are located. And then in the area 1 here is where Stereo A is located. And when looking at this blue cone here, that's going to give us the time series and also show us the CME path. And in this work, we're going to focus on the Omni time series and remote sensing observations from SDO, SOHO, and Stereo A. So in thinking about the filament that was on the sun, we can see it here. It's darker than the surrounding area, but obviously brighter than space. And we're going to be looking at this in the ultraviolet. If you look at the timestamp here, we got this time at 5:22 a.m. So what is a filament? A filament is a cool, dense plasma that gets stuck by the sun's magnetic field. If you look at the first picture on your right and picture A, we see the positive going into the negative, and this is on the sun's surface, and those are the magnetic field lines, and then we have the plasma being stuck in the middle. And when looking at photo B, we also see, instead of it concaving and the plasma being in the middle, it's just sitting in a dip, and then we also have our flux line going in the middle of that. Now when looking at this photo over here, we have our axial flux on the ground and our palladial flux going over our filament, and while the sun is rotating, this is causing the magnetic field to twist and turn, leading to the filament erupting. So to model the magnetic field, I used a nonlinear force-free field model using Coronal modeling software. And in the first photo, the red represents positive and the green negative. So imagine those photos I told you earlier about the positive going into the negative. And then of course we have our flux rope, which is that blue line going in the middle of the filament. And over here, I did create a cross section, which we'll be looking into this filament to see if it erupted or not. So these are our results. In this particular filament on your right, it was unstable, causing an eruption. This particular filament on your left is actually still, it's not the best stable filament that we have, but it was the closest one after testing 50 different models. And we are looking at these models in the Z of S axis. So then we get to our CME in white light, and this is also going to show you the density here. And we're looking at Stereo and SOHO. However, we can only see this in 2 dimensions, which is why we decided to look at the croissant model. And looking at the first photo, this basically shows you kind of where that filament is going out to in that flux rope area. And then we are doing, this is basically geometric modeling from 2 different perspectives, looking at Stereo A and SOHO. And how did we do this? So we decided to fit the croissant shape to our CME that we observed at 6:37 a.m. And the croissant has to cover the density feature we observe in the coronagraph images, and we can change the half angle, height, aspect ratio, latitude, longitude, and tilt angle. The results of the gradual cylindrical model that we can see, obviously I noted the different timestamps so you guys can see the different perspectives. And We triangulate the C2 and Core 2 images when implementing the model from 2D images, as you saw in the white light, to the 3D structure of the CME. Now, and this model is giving us an idea about the size, speed, and direction of the CME, and it also shows that the CME is not changing considerably, therefore making it a great candidate to reach our planet. So to understand the CME after lunch, we want to get the time that it takes to reach the Earth, meaning that we need the transit time. The way that we're going to be able to do this is by understanding and using the working surface model. So when looking at that image over there next to the sun, so we understand that our filament erupted, and therefore now we have a CME. This CME is going at supersonic and superalphonic speeds, and since the solar wind is going slower than our CME, it creates this working surface. This working surface slows down the CME while propelling the solar wind forward, and during this time, the working surface is actually eating the mass from the CME. However, the CME's mass is finite, and is also eating mass from the solar wind. However, that is infinite. So there will be a point where, in the second phase, where the working surface will start to decelerate. So within the working surface model, CMEs are studied as constant perturbations in the solar wind. Looking at our first graph up there, we see the velocity times the speed of A, which is basically the velocity of the CME coming. This creates the current velocity of the CME, and then when it starts to decelerate, we go back down to the constant speed during a duration of time. And we also see this with the mass loss rate times B and the density times C. The model relies on solar wind and CME quantities. We can get the CME information from the coronagraph observations. When looking at these equations down below, we see that these are heavily reliant on A, B, and C. With that, we need 6 variables, and right now we only have 4. So how are we going to do that? Well, we need the mass loss rate, and we need to get the velocity. First, when thinking about the mass loss rate, we need to understand what a streamline is, and it's a plasma path that is not dependent on time, and energy and mass are conserved. We also assume that this is an adiabatic plasma, which means that there is no heat exchange from the plasma and the environment, and also the temperature and magnetic field changes are neglected, which gives us the mass loss rate equaling the density times velocity times 4 pi r squared, which the 4 pi r squared represents that it changes with the sphere size. So then coming to the Poisson adiabatic equation, the equation assumes that the adiabatic process combines the first law of thermodynamics, which again means that energy cannot be created or destroyed, the ideal gas law, and the capacity radio gamma, which gives us the equation down here. Basically, when looking at this equation, we are only looking for V0 right there, which is the solar wind, while everything else is given. So when we input this data into Python using SciPy ODE, we get these values here. So again, when thinking about predicting the arrival of the working surface, at the first stage, we're moving at a constant velocity of 937 kilometers a second, and that is until 21 hours or 116 solar radii. And then after I said the working surface has eaten the mass of the CME, we go all the way down to a velocity of 833 kilometers a second, and we are predicting that it's going to hit Earth after 46 hours. And so we are predicting that the CME will arrive at Earth about 2 days later at 3:37 UT. So when looking at this data plot first, in the first graph we have magnetic field in the Bx, By, Bz. Then we have magnetic field and temperature, velocity and density, and CMH at the bottom. The dashed line here in the graph shows our prediction, and the reason that our prediction is off is because we have to eyeball a lot of things. Like in the first images that you saw where we said 522 and then 637, so that is why our prediction is off here. Now, when looking at when the working surface and CME actually arrived, in this red highlighted region over here, that is our compression region, which you can see an enhancement of the density, velocity, magnitude of the magnetic field, and the temperature. And then when the CME hits, and remember I was saying how the mass was going to be eaten, therefore we see a decrease in our density, our temperature, and we also see a strong magnetic magnitude of the magnetic field, which leads to having a very low BZ component allows us to have a very low CMH component, which gives us an intense geomagnetic storm, meaning that it needs to be below -200, and ours was -335. So basically, we need a coherent magnetic structure, a strong negative BZ component, and high speeds. So what is the CMH again? Basically, this measures the strength of the geomagnetic storms by tracking the horizontal component of the Earth's magnetic field. And we can see this when we have changes and disruptions in things like power grids and communication networks that are impacted by the solar wind. So when going back and thinking about the filament again, we started out with the filament being at the sun, which became a CME, which we observed with this croissant model, and then the filament at Earth as the CME right here. And the filament is recognized by the components of the magnetic field going from positive to negative values. And the magnetic field strength of the filament is 40 nanotesla, and the BZ is -40 nanotesla at a certain time. However, if you also look at this graph again, you may have been confused when you saw the change right over there. And that is because another CME was recorded. However, that one flew by the Earth, but as we see, it still impacted the Earth's magnetic field. So some conclusions. This is a case study about a lot of CMEs. However, this one came from a filament, and I used the NLFFF model to understand this particular filament's magnetic field. And I worked with the working surface model to estimate the CME transit time from 15 solar radii to 1 AU. And then we also estimated the solar wind speed and mass loss rate back to 15 solar radii, assuming the solar wind is a result of the expansion of the adiabatic plasma to connect our inputs to the outputs. So for future work, comparing the NLFFF magnetic model field lines with the EUV models 1-to-1 to see how our magnetic models are doing, then analyzing the chronograph images to estimate the speed, direction, and mass of the CME, including these remote sensing observations, including stereo A and in situ analysis, and analyzing deeper in the in situ analysis to determine the flux rope boundaries, which will allow us to perform 2D and 3D MHD models, and then also including the previous CME analysis in terms of its geoeffectiveness. And I would like to thank everyone for helping me out. And yeah, that's all.
All right, another efficient talk. So, let's get started with questions. And a reminder to people who are watching on the YouTube live stream. So even though it says chat is disabled, or comments are disabled, there is a live chat, and that's where you should actually be putting your questions. And immediately we got a comment here from Ed DeLuca. Congratulations on the successful combination of analytical tools. Can you describe in more detail how the NLFFF simulations are used to establish parameters for the CME model?
So basically, we insert different polygial and axial fluxes to test whether the filament will be stable. Does that answer their question?
Ed, does that answer your question?
Well, and basically, we did 50 different models, going from the values that you see above.
It's a bit of a lag. It might take a bit.
Here, I'll follow up.
All right, Kathy's going to follow up.
So just to follow up on Ed's question, once you found the unstable, I assume you're looking for the unstable filament because it did erupt, right?
We're looking for the stable.
Oh, for the stable.
Yeah, right before eruption.
Okay.
That's what we wanted. Okay, so basically, if we're able to see the stable filament right before eruption, in the future, when we're looking at other filaments that did erupted, we can look back and see, okay, were the magnetic fields the same here? Was the magnetic field construction the same?
Okay, so did you use these numbers in anything in the later modeling, or was this sort of a separate exercise? I think that's part of Ed's question there.
Actually, Ed says that on the next slide is, I think, what he's looking for. Or maybe not.
I think like maybe I think but he asked like from
Hold on.
NFF model what we use the parameter for
Repeat that
analytical
again.
model, right?
Repeat that again.
Oh, sorry. So I think like Ed is asking is from NFF model, what is our input for the analytical model, if I do understand correctly. So we haven't done that.
Yeah.
So that's two separate things we're doing right now. Magnetic model one side and analytical is different.
All right, looks like Ed is satisfied. So it's a brave new world we live in. Technology's every aspect of our lives. All right, more questions. All right, over here.
Hello. That was a great talk, amazing talk. And I have a question about, I think towards the end you talked about like the compression, like there's like a compression of the magnetic field and also like the other graphs. So can you talk a little bit more about what happens when you have that compression zone?
Yes, I can. Okay, so in the compression region, which basically, so imagine the solar wind, and then the working surface, and the CME is behind that, and the working surface was propelling our solar wind forward, and that is why we have and basically think about the working surface that has a lot of density because it was eating a lot. And so that's why we see the enhancement of density, and it was moving faster than the CME, and also we have an opposite magnetic fields from the solar wind and the Earth's magnetic field, which is why we have this compression, which if you look at this video here, can you see it kind of compressing? Yeah.
The one from the Earth magnetic field?
Yeah.
Oh, okay.
Mm-hmm.
Thank you so much.
Torsren.
Great talk, Sitara. So now that you know, so you had your prediction of when you expected this to come in, and it was off by, that looks like
About 10 hours.
about 10 hours. Okay. Can you go back to the not slide-wise, but like, can you go back to the like pictures that you had of, or the data from the, I think it was Parker Solar Probe and other satellites that were closer to the sun, and see if you can get it to match up with when you actually saw the CME arrive? So like, I don't know, if you predicted when the CME would arrive based on data from probes close to the sun, and then it was off, it was like, it was later than you thought it was. Can you like look at that data and see if that still makes sense?
Yes, so in the future, we were thinking about using Parker Solar Probe data and seeing if our transit time prediction gets better. Does that answer your question?
I think so.
If it doesn't, just ask another one. We got time.
Yeah. Yeah, I guess, can you still rationalize the data that you got from like Parker Solar Probe and what was the other probe that was close to the sun? Or was it, yeah, there were two probes that were close to the sun. Yeah, solar orbiter. Like you predicted the velocity based on those two, right?
No, we just used SDO, SOHO.
Oh, I see.
So we did not use the other satellites.
I see. Okay, I think that answered my question.
No spacecraft.
Cool. Okay. Thank you.
Okay, there's someone in the back.
All right, Jonathan.
Hi, Jonathan.
Hi there. Just to follow up on that, I mean, well, I know you had the prediction of the arrival time.
Yes.
You didn't quote any uncertainty on that, right? So presumably there's an uncertainty on the velocity that comes from there, and so I can't tell whether I should be surprised that there's a 12-hour difference. Like, we were expecting it to be within 10 minutes, we were expecting it to be within an hour, or is a day good enough, right? So it might be helpful in future work to try and add uncertainty estimates on the propagation so that you can see how surprised you should be.
So currently our uncertainty, I agree with you, currently our uncertainty is plus or minus about 8 hours.
Okay.
Now we did not have the mass So we went back and saw other data looking at LASCO, and we kind of saw what the mass was in the past, and so we approximated that. And then we did have to eyeball where this was. We had to the filament, and then we also had to eyeball where the CME was, and we started at 15 solar radii. It could have been before that, could have been a little bit after that, but a lot of things were eyeballed, which
Okay, so
was
that
why
you
we
need to
had-
add those into your error budget and
Yeah.
to estimate the overall error. Yeah, okay, thank you.
And so those are some things that we can fix in the future.
All right. Nick has a question.
So, for your magnetic field measurements,
'Kay.
do you know how those measurements were done, or at least which instrument made them?
For
For like when you measure the like the magnitude of the magnetic field, when you're talking like on your slides to deal with like the compression and stuff, I think you had some.
Okay, now can you re-ask your question? I'm so sorry. Okay.
Yeah. Do you know like how that magnetic field magnitude was measured, or at least which instrument made the measurement?
No.
Okay.
And I think I can take one more question. We got 2 minutes.
Oh, we got a lot more than that.
Oh, I didn't know. Never mind. 7?
No, we got 2 minutes.
Oh, we got 2 minutes? Oh, yeah. Oh, yeah. It's 10:30, not 10:35.
Oh, there's one more though. There's one more.
Chris Moore topping it off.
What do you think the impact of this work is for future space exploration in the solar system?
I think predicting the time a geomagnetic storm will hit the Earth will allow us to power down instruments beforehand instead of destroying technology getting disrupted and getting destroyed.
So in addition to Earth, what about the rest of the solar system?
I haven't even thought about that. That's a great question. Yeah, that's what I was going to say.
Well, you could do the same analysis in a different
Kathy,
direction.
microphone.
Ooh.
You could do the same analysis in a different direction, right? If you had, Parker Solar Probe off somewhere else where you could get measurements like this to feed your analytic model. If you had astronauts going to Mars or something, and you had Parker Solar Probe or stereo or something out in the, off the line with Earth, you could probably do the same analysis in a different direction, would be my guess.
All right. And with that, let's give Sitara one more round of applause. All right, we're going to enter into a 15-minute coffee break just so everybody can get the caffeine and calories necessary to push through the day.
I think for coffee you have to go downstairs.
Yeah, Kathy, you have to for coffee you have to go down. You have to go down to our fancy little coffee machine in the lobby. Please.
It's a pastry break.
Yeah, it's a pastry break. All right. And speaking of pastries, for the love of God, please eat them. There's so many of them. All right. We'll see everybody back at 10:45. Probably good enough to do some introductions. All right, coming up next, we have William Keener. He's coming to us from Austin Peay State University down in Tennessee. And he is going to talk to us about everybody's favorite topic, at least if you're a physicist, turbulence. So, whenever you're ready, take it away, William.
So, I'm William Keener from Austin Peay State University. I'm going to be talking to you about the stream evolution of turbulence observed by Parker Solar Probe. One of the biggest open questions in plasma physics is how the solar wind is heated. This study is meant to examine two different components of that solar wind heating: ion cyclotron waves and turbulence. But we didn't get to ion cyclotron waves yet, so we're just going to look at turbulence today. There is a quote attributed to Werner Heisenberg. Supposedly he said it on his deathbed, that when he dies and meets God, he's going to ask two questions: why relativity and why turbulence? And he's only going to get an answer to the first one. So that shows that turbulence is a widely misunderstood phenomenon. That being said, it is stochastic. It is statistically determinable. And it is one method of plasma heating. One of the best methods to analyze that is within the solar wind itself. A turbulent cascade generally follows this pattern. We have some injection scale with a large energy throughput, and we have the inertial subrange, where the spectral slope falls off at the same rate the entire way through, until we get down to this dissipation range, where some of that energy turns into heat. This was first proposed by Andrei Kolmogorov in 1941, and that energy cascades from large to small eddies in the inertial subrange at a constant rate. That rate is at a rate of -5/3. In plasmas, there is a slight modification, though. It changes to -3/2 due to magnetic field effects. It's a bit of a math jump scare, but it's not actually that bad. We have the velocity change over time, as well as nonlinear terms, pressure gradients, and a viscosity symbol. And we have the magnetic field change over time with still coupled velocity and magnetic field components. We are going to apply two constraints. One, that we have no magnetic monopoles, so divergence would be 0. And one, that we are in an incompressible plasma, so the divergence of the velocity is 0. And this is just highlighting those terms individually. We have the nonlinear term within velocity that actually drives the turbulence. We have magnetic tension, which enables those alpha vane waves, which we'll get to in just a moment. We have viscous resistive dissipation, and we have the stretching of field lines by the flow of the plasma. All terms couple velocity and magnetic fields, so the energy can transfer between them. Alpha vane waves. One type of alpha vane wave is the Alsacer variables, essentially fluctuations moving toward and away from the sun. This has a nonlinear term that requires both z plus and z minus. But when z minus goes to 0 or z plus goes to 0, we have what is known as imbalanced turbulence. And that's the turbulence that we actually care about today. So this nonlinear cascade goes to smaller scales, as I mentioned before, and we have the damping of fluctuations, and the pressure gradient maintains that we don't have an extra energy source in the system. This imbalanced turbulence depends on the population of those Alsacer variables, those fluctuations in magnetic field and velocity. The helicity barrier is a theory that's been proposed in recent years at the cross between the inertial range and dissipation range in the slope spectra. Essentially, that helicity barrier is in a transition region where the slope increases its magnitude from -5/3 to some larger value. The helicity barrier is something that inhibits that cascade. When cross-helicity, the correlation between magnetic field and velocity fluctuations is really high. And it requires that imbalanced turbulence, so that Z minus term, 0 or very close to 0. Similarly, ion cyclotron waves arise at these kinetic scales, and that is the other method of solar heating this project will look at in the future. That spectral steepening of the slope marks that onset of the dissipation range. So to analyze Parker Solar Probe data, we have to get rid of the noise and smooth everything out and analyze what those spectral indexes, the slope, actually are. In this case, the slope was at negative 1.62, so very close to that 5/3 power law. And then looking at the cross-helicity, we see that it's really high for most of the frequency range, and that the residual energy is really low. Essentially, residual energy is just a measure of how kinetically or magnetically dominated the plasma is. We get this data by using two instruments, specifically the SPC in the Solar Probe Cup in the sweep suite that gives us our plasma measurements, and the magnetometer, the second magnetometer in the field suite that gives us our magnetic field measurements. We want to pick turbulent regimes within fast radial scans when we're moving radially in or out of, or away from the sun, so that we are in the same plasma stream the entire time. So first we have to apply some filtering and then sync that magnetic field cadence to the velocity cadence. The magnetic field data is returned at a higher rate, so we have to interpolate onto velocity. And then we apply wavelet transforms to smooth that data and remove noise. In this process, we also had to do additional filtering. Parker Solar Probe has two modes that it goes through, full scan and peak track. When we are in full scan mode, we get these resonances here towards the end. Those are a product of swapping modes, and as a result, we have to remove 1 in every 32 data points. And then we also have to remove noise. One example of that is with the reaction wheels. They have a set frequency that adjusts, and we can see the aliasing effect in our scalograms and our spectra. We have two intervals of the fast radial scans for every orbit. So we can, and they range from around 19 hours to around 53. So we have to window those time segments appropriately. We chose 1 hour windows because that is well within correlation rate for if we were in the same plasma stream, as well as we don't want more than 10% data missing from the SPC or 1% of the data missing from the magnetometer. So taking a look at the cross-helicity, which is, as I said before, a requirement for that imbalanced turbulence in the helicity barrier, we can see that most of our windows have a pretty high cross-helicity magnitude. As we move left, the fluctuations are anti-correlated. As we move right, the fluctuations are more correlated with each other in magnetic field and velocity. And then as we move up, we're in a more kinetically dominated plasma. As we move down, we're in a more magnetically dominated plasma. This plot shows the amount of scans, or amount of windows in the scans, whether we are moving away from the sun in the blue, or in the red, or if we were moving toward the sun in the blue. So applying our filters to that, we want to make sure that, once again, we are in a magnetically dominated plasma, so our plasma beta value has to be really low. So we rejected some of these windows because of that, and we rejected others because the cross-helicity was not high enough magnitude. Looking at the power spectra that we get from that, we can see that this is the magnetic field, and that 5/3 slope, this black line here, matches fairly well, but if we look at the 3/2, it matches much better to our mean value, our mean and median values, really. This is a result of all 260 valid windows plotted on top of each other, and at 1, we've normalized it to be the inertial length. Similarly, in velocity, 5/3, it's more steep than in actuality, but 3/2, that adjustment fits much better. And here's 4/3 to make sure we weren't underfitting or overfitting it. In Z plus, the Alsacer variable moving away from the sun, we can see that 5/3 is way too steep. 3/2 is a little bit better. 4/3 overfits a little. And Z minus, the one with the most difficult resolution of them all, you can see that curve, that fall off within the data better than the others. The 5/3, way too steep. 3/2, a little bit better, but 4/3 is most accurate for this one. Looking at our cross-helicity, we see that over time it decreases, but for the most part, we are in a really high cross-helicity range for those valid windows, and the residual energy increases starting from a relatively low point. Our next steps are to down-select the datasets based on stream quality, so to make sure we aren't in a CME event that would change the turbulent regime we're in, as well as analyzing the moment versus the fits data. Everything I showed you before was for moment data, which falls off at a slower rate than the fits data. We can expand to more fast radial scan intervals or windows, so we can, instead of choosing 1 hour, choose 3 hours or 2 hours or 30 minutes. And then finally expanding to the ion cyclotron waves, you can see a typical turbulent cascade with a reaction wheel tone. But if we include the ion cyclotron wave data, we get a bump in the spectra here, which we are currently not able to resolve on our interpolation bounds. So here's a value reporting the median. Here's a table reporting the median slopes for that, and we can see that we are in fact in a magnetically dominated plasma because the slope approaches more so the Orozhnikov-Kriegman scale. Acknowledgements. And any questions?
All right, thank you, William. All right, who wants to start off questions? Kathy would.
So now that you've determined your slopes for the turbulence, how would you relate that to this heating problem in the solar wind? Do you have a inkling for how that connects?
So it's important to look at that transition range because that is where the heating would start to occur. So once we get into the dissipation range, that's where heating starts to occur. The helicity barrier prevents us from doing that. As we move forward with the project, we would be using span data to correlate the temperature of the solar wind with the turbulence or ion cyclotron waves.
Question over here.
Great talk. I am curious about what kind of simplifying assumptions you might have had to make. I think on slide 4 you mentioned something about assuming a few things, the constraints, and I'm wondering in the range that you were looking at, are those usually pretty good? Is there anything that like a more advanced reading would get you if you didn't have to make those assumptions?
So the magnetic monopole one's easy to explain. Those don't exist in functionally anywhere. There's like one crystal. But as for the incompressible plasma, alpha-vane waves by nature are meant to be incompressible. We know the solar wind itself is not wholly incompressible. It has some compressibility to it, but there's, like the Elsasser variables themselves, alpha-vane waves are not meant to be compressible.
All right, Ed DeLuca is back with a question online. So the residual energy was negative on one of the plots. What does that mean?
A negative residual energy, it's essentially that the magnetic field component of the equations is a greater positive magnitude than the velocity component. So, yeah. We can see that it increases, so we are gradually becoming more kinetically charged than magnetically charged. But having a negative residual energy is actually good for the study.
We have Yami back here, and then we're going to go back to Ed for another question.
Is it a follow-up question? Because I can wait. Okay. So back to the previous question, which I thought was really interesting. I was wondering if, in terms of your compressibility, if that's something that you could validate. So could you compute compressibility? The compressibility degree of your plasma?
It's possible. I don't know how I would do that at this time.
Yeah. So we're going to go back to Ed. Has a second question. He's really laying them on right now. Is there evidence for inverse cascades in these data? Does that have implications for the inertial range slopes?
An inverse cascade, like having a positive spectral slope instead? Is that what he means?
I'm not sure.
We'll wait like 20 seconds.
Okay. Any intervening questions? Over here.
Okay, this one is hopefully really simple. It's just, I know that there's a general positive increase, but then there's a drop right between 10 to the negative 1, 10 to the 0. Can you just explain what that drop is and why it does that?
Like here?
Yeah.
So part of the data is like misadjusted. There are areas that have like 44 points or versus 48 points. Most of these are the ones that have 44 points. So this drop in the median value is just because those traces end.
Okay, Torsren.
Hi. Does the Kolmogorov cascade, is that what defines like some turbulent phenomenon, or is like turbulence better defined somewhere else? I know that you said you jump out the window if we asked you to define turbulence, but
it depends on what fluid you're actually in. So
Okay.
the Kolmogorov cascade states that in the inertial range, we will be breaking down into smaller eddies at the same rate the entire time. So with a typical fluid, a hydrodynamic fluid, it would be that 5/3 power law.
cool. Thank you.
All right, we got clarification from Ed. So he said he's talking about the formation of coherent structures, so energy transport from small scales to larger scales. These are typically associated with helical structures or solitons in fluids. Does that clarify?
Like,
would you like the original
like
question?
we would have more energy injected into the system in order for that to happen.
I think he's mostly concerned with, instead of going from large scale to small scale, going the other way. All right. Michael's going to bail you out.
So Ed, that's a great question. So the idea with the helicity barrier is you have a balance of general helicity, which in the inertial range, as William was talking about, that's cross helicity. But as you go to kinetic scales, that's magnetic helicity. And the idea of an inverse cascade, as you're mentioning, is talking about magnetic helicity. You have all these small scale magnetic islands that can kind of braid and twist together, and you get from small scale to large scale. And that would be something that would happen in the dissipation range, and that would be your inverse cascade that would come up and balance your inertial range cascade. And that's the theory behind the helicity barrier. So the slopes we've been looking at, they should be something around a minus 3/2, which is predicted by the helicity barrier theory, which would be consistent with possibly that inverse cascade coming up and balancing the turbulence that we see. So, yeah.
Any more questions? Oh, back here.
It was a really good talk. Could you go to the plot where it matched to the negative 4/3 slope? So for this plot, you mentioned that this could be due to like the instrument data that you were getting. Like there might be some other factors. So would it be possible to like rerun or like do some adjustments for the way that you're filtering the data from the instrument to get it to match to that negative 3/2 that you want it to match to?
For Z minus especially, no.
Okay.
It is much harder to resolve that since that's what's moving towards the sun, and we are also moving towards the sun. Like our measurements are coming at us, and we're supposed to measure something going away from us. So that's one of the main issues with that, outside of just instrument noise picking up.
Thank you.
Time for probably one more. Kathy.
For some of these plots, you mentioned that the 4/3 slope was overfitting the data. Could you explain a little bit more what you mean by that?
Yeah, so the final calculated slopes were here. You can see that the 4/3 is most close to the Z minus spectrum, but the Z plus and the velocity have less alignment with that. They are closer to the 3/2 power law. So an overfitting of it would be we're going too far up as compared to too far down.
Gotcha, thanks.
That was shorter than expected. One more question? Oh, Chriselle beat you by like a hair.
It's just an
All
arbitrary.
right,
Yeah.
Sorry, no, I meant like the number, because I can't do it in my head.
1.333.
1.33, okay, great.
All right, we got through that. So here's Chriselle.
I was wondering about your uncertainties. If you had like an idea of how big your uncertainties might be with with these slopes, like are they gonna be symmetrical, or is it gonna be more to this 5/3 to 4/3? Where do your uncertainties raise with your slopes?
So we are expecting them to be around 3/2. The range I actually did the calculation for that median slope on at the end was between 10 to the -2 and 10 to the -1, because that's where we have no like data issues on either side. Like all of the runs are still there, and we're not experiencing this spike from the injection.
All right. And Ed had another question, but he's too late. So, so everybody, let's thank William.
How's that?
Woo! Other one? Okay. On the right, because you're going to be turning your head a lot. Yeah. Okay, how's that? That good? Yep, perfect.
All right. Up next is the winner of the annual award we give out for the applicant with the name that goes the hardest. So this is Torsten Diesel. He's coming from the University of New Hampshire, and he's going to talk to us about CCD's kind of next step up, and that's the CMOS detector. So with X-ray applications. So go ahead, Diesel.
Cool. Thank you very much.
Or Torsten.
Hi, everyone. I'm so excited to talk to you today. I'm Torsten. My advisors are Chris Moore and Jason Hong. And today I'm going to be talking about CMOS detectors. So in a nutshell, I want to help understand the quirks of our particular X-ray source in our lab by using a commercially bought, well-characterized X-ray camera. So solar flares are too bright for our current X-ray detectors. That's the main issue that we're having. So the detail and artifacts of high-energy X-rays, details is lost. In scientific information was there, but it was just the solar flare was too bright, and so we lost that information. There's two phenomena that are happening here that are interrelated. There's blooming, and there's oversaturation. So that's like charge spilling from one pixel to another. And then oversaturation is if you think of the pixels like buckets that hold charge, the buckets overfill. And the reason for that, one primary cause, is just slow readout in CCD detectors. So for example, the AIA detector has a readout of only around once every 10 seconds, depending on the wavelength. And so one way that my advisor and his compatriots have tried to fix this is by using CMOS detectors, which in the SAXI rocket, so that reads out, they got a readout of 6 hertz, which partially mitigated that issue with slow readouts. And that's just so that you can see the blooming effect that we're talking about once more. And just to underline how important this topic is, in the decadal survey that came out early this year, they actually explicitly called out high dynamic range short X-ray imagers with CMOS detection. So how do these two things that we're using work? There we go. Okay. So CCDs, they both collect light the same way by the photoelectric effect, but the CCDs actually kind of just shift the charge in and out, kind of in a single file line, which, so the charge is converted to a voltage here, and then this voltage is then converted to a digital signal with an ADC. In CMOS, each pixel has its own amplifier, so we're not losing information by moving charges around or anything like that. We're actually converting it to a voltage right then and there, and then each row can be read out as a digital signal from there. So to just reiterate that, so CCD stands for charge-coupled device. First, photons are absorbed into the silicon via the photoelectric effect. The number of electron-hole pairs is proportional to the energy of that incident photon. Charges are then shifted from one pixel to another by an amplifier, and that amplifier converts the charge into a voltage. And the voltages are then turned into a digital signal by an analog to digital conversion. CMOSs, or complementary metal oxide semiconductors, the first two steps are extremely similar. The photons are absorbed into the silicon, and then the number of electron hole pairs created is proportional to the energy of the incident photon. But then those charges are immediately converted into a voltage using an amplifier on each pixel. And then each row of the detector can have its own ADC that it reads out to. And so some of the benefits of both of them. So CCDs can produce higher quality images, but CMOSs have faster readouts, as we've seen with SAXI rocket. CCDs have a bit of a higher sensitivity, but CMOSs have a better dynamic range. But CMOSs are more power efficient than CCDs, are generally less expensive, have a more compact design, and at the cost of being a little bit noisier. CMOSs are also especially appealing because they tend to be more radiation resistant. So rhetorical question, how can you tell if a camera is working? Just in general, right? I take a picture of, say, this picnic bench outside the dorm that I didn't get locked out trying to take this, like yesterday, and take a picture, how can I tell that that picture is actually what is represented by reality? And the answer to that is, like, if I have two detectors, one being my eyeballs and the other being my phone camera, and they line up, then we know that that's probably what's there, that there's probably a picture match there. More difficult question, how can you tell if a camera is working if the light you're trying to detect is invisible, right? We've seen this plot a lot. This is the electromagnetic spectrum. This is all the light that we can see, right? But we don't see any of the X-ray stuff. We can't, of course, we can't see the radio waves, right? So how do you tell if a camera that detects invisible light is working? You actually do it the exact same way. So if you have another camera that can also see X-rays, then this impossible task becomes possible. And this generalizes just in science, like in anything in science, to if you have like two instruments, they should match up. A meter stick and a ruler should give the same measurements, right? So our experimental procedure, very broadly, we're starting with an uncharacterized X-ray source, right? And a well-characterized X-ray camera. We take X-ray pictures of the unknown X-ray source, and we use that data to characterize the X-ray source so that we can begin testing new CMOS detectors for future flight missions. So here's the camera itself. It's an Andor Marana X S-CMOS camera. The S just stands for scientific. It's like a branding thing. But yeah, so that's the pixel sensor. This is a beryllium filter, and that's it attached to our vacuum chamber. We're not going to fly this. This is not designed to be used on a rocket. It's too bulky, but it's perfect for our use case. Our original camera had a pixel width of 11 micrometers, but we had some internal camera issues with the circuitry. And so we borrowed Suzanne Romain's, which had a pixel width of 6.5 micrometers instead. And it actually uses the same technology that is in many phone cameras, right? Because like a lot of phone cameras also use CMOS detectors. So you might be carrying a CCD detector right now. Another fun fact is that it costs $65,000, which is about 8 times my net worth. So I'm very glad I didn't drop it. Yep, I know. So here's the XCF, the X-ray calibration facility that we're working with. So here's the Manson source that we have, which emits the X-rays itself. I'll explain how that works in a little bit. But basically, X-rays are emitted isotropically from this thing, and they hit this detector, which is we understand well. And then this is the CMOS detector. And then here's an actual picture of it. So this is what it looks like in the lab. And then all this part is under vacuum, all this like highlighted bit. Yeah, so this is the Manson. This is Charles Manson. He has nothing to do with the Manson X-ray source. We don't like him. But this is the Manson source. So electrons are accelerated here through an applied voltage on the order of about kilovolts. I think in the measurements that I'll show later, we did it at 9 kilovolts. Electrons interact with the anode material, which we can choose by like spinning it around. And they release X-rays in particular wavelengths characteristic to the material. The X-rays scatter isotropically. Some will travel down the path towards the two detectors. And these filter slides just filter out visible and ultraviolet light, and as well as Bremsstrahlung. If you're not familiar with what Bremsstrahlung is, in this experiment, what's emitted from the Manson source will look like this. These are the lines that we care about, but this is like braking radiation. So when an electron passes close to a nucleus, it'll slow down almost like car brakes, and to conserve energy, it emits a photon. So instead of calculating what energy we predict, we just referred to this table provided to us by the lovely folks at Amtech. And we care in particular about the titanium lines. So I zoomed in here. If you're not familiar with X-ray notation, the K alpha line is kind of like the first series in the Lyman, the first entry in the Lyman series. So we have K alpha and K beta. Those are the ones that we care about. And so we have 4.5 keV and 4.9 keV. So let's revisit this. So my project, in a bit of a thicker nutshell, is to characterize the readout rates, the dark currents, the spectral resolution, and the noise profile of a commercially available and pre-calibrated CMOS detector, specifically the Marana X S-CMOS from Andor Technologies. And then we use that, future projects will use that information to further understand our lab's X-ray source. Anyone have any questions up to that point? Cool, okay. It's not too late to switch to theory. That's what we were thinking, like, literally about a week ago. We still hadn't we got data last Thursday, so yeah, but it was very much a crunch. There was a ton of stuff that went wrong. First bit, we had somewhat incompatible vacuum parts and flanges. So the Andor CMOS's camera performs as temperature decreases. It likes it at a nice, chilly, negative 25 degrees Celsius or colder. But since water condensation on the surface of the sensor is catastrophic, the camera must be operated at extremely low pressures. So we pumped this vacuum chamber down to 10 to the minus 5 millibar, which is 100 million times less pressure than in this room. Creating a high vacuum like that is tricky, but attaching something to that vacuum chamber is trickier. So we have two tools in the trade. We can either use gaskets or we can use O-rings. I'll start with O-rings because they're the one that we didn't use. They are like a squishy donut. They fit in between the thing that you're trying to attach and the vacuum chamber. You just screw it real tight, and then it is malleable, and so it kind of fills in all those gaps. And then this is the gasket. So it has, so I actually brought one. It has a little gap here, so you get, you can always tell when there's a gasket being used because like the gap is very small. There's knife edges here that kind of dig into the copper and is very malleable, and so it produces like a very good seal. The problem that we had was that we had the knife edge seal on one side, but we had the flat side on the other due to, like, we just didn't notice it. And so when you look at this, you'll see that there's a knife edge on one side and it's flat on the other. So you can just pass that around. But this is us installing the camera onto the vacuum chamber. So that's me. Then that's us attaching it. And thankfully, it works like a charm. So bit of a rhetorical question. I guess not rhetorical, what do you guys see here?
X-ray photons.
Yep, sure do.
A handful of X-ray
a handful of X-ray photons, that's exactly it. So just to point them out, they're all the little white specks there, and then you can zoom in, and that's what they look like. So that is a single X-ray photon, which I just think is so cool. Another thing that you can see if you're looking really close is that there's actually these horizontal lines that you can see through here. And that's something called the fixed pattern noise, which is due to like a bias in each of the individual pixels of the CMOS sensor. And so when we do the analysis, we want to characterize that and subtract it out. And so this is what the fixed pattern noise looks like. You can see that we have these horizontal, some vertical lines going through, some horizontal lines. So each pixel in the CMOS sensor may have its own bias. So we want to characterize the noise on the amplifier. This image is produced by, we took 100 frames of darks, so no X-rays were here. And we took the median value on each pixel. And so when we do proper analysis, we will subtract this pattern out to get normalized data points. Another thing that happened, because the pixel size is actually so small, we have to do another processing layer called grading, which is basically like if we were to histogram all of the rows in this pixel, for example, we would get multiple different values. This is a single event, but we want to consider it as a single event, not as 4 events like those pixels. So we just kind of bin them, and then we integrate over all of those bins. So the result of all that, after we do all that, we get this lovely looking spectrum. Remember, we were using titanium, which had energy that we wanted of 4.5 keV and 4.9 keV, which looks pretty close to that. So this is from 100 frames of titanium X-ray emissions, each with an exposure of 0.1 seconds. Since we know the energy level should be, we can fit that as a curve onto our spectrum using like a summed, like double Gaussian. And that lets us figure out the energy, and that lets us in turn figure out the gain and the bias of the detector. So here's the Gaussian fit that we used, and then the difference between this plot and the next one is that this one actually has energy as its x-axis. So this is when we scaled by the energy. So the conclusions, we performed several measurements using a commercially available CMOS camera with the intent of using that data to eventually characterize the Manson source. This particular system performs phenomenally, but it was borrowed from Suzanne remains due to internal errors in our own original camera. So we want to redo these measurements when we get our own camera back after the manufacturer does some repairs on it. And then once we can properly take X-ray images of high-energy solar flares, that will greatly aid our collective mission as solar physicists to understand the mechanisms which drive them. Here's some sources that I used. And these are all the lovely folks that helped me. Thank you all very much.
All right, we have Lisa Diesel in the chat, and all she says is Diesel. So I assume that's just how you two Diesels greet each other.
Yeah.
Okay.
That's how we say hello in our native language.
Got it. So Ravina Khan has a question. Switching from a camera with 11 micron pixel size to 6.5 micron pixel size, what difference would you see in the results, if any?
Yes. So the main difference that we would see is that we wouldn't have to do as aggressive grading. So this is a considerably nicer, actually, event. But we had some events in this series which, like, the pixels were, like, you know, in a 3x3 grid, or even like a 4x4 grid, where like we would have to do some kind of grading, like the. And so if we had a larger pixel size, all that would mean was that we wouldn't have to do grading as aggressively. Yeah, like it would wind up. We might even get like some events that just covered a single pixel, but instead, like this introduces some uncertainty, I guess.
Jenna.
Thanks. Nice talk.
Yeah.
I have a question about CMOS technology. You mentioned that it's noisier. That's the one downside. And then you showed the fixed pattern noise, which I assume is due to the different ADC gains. I was wondering, is that what you mean by noisier? Or is there also some temporal noise that you can't just subtract out that's increased compared to a ZCD?
Yeah. So CMOSs have more, I guess the more precise way to say that is that CMOSs have more sources of noise. So we didn't have enough time to characterize all of them in this sensor. But for example, there's the readout noise, where like on each pixel, if you take a 0-second exposure, you'll have some baseline noise from that. Another example is this fixed pattern noise, where this might be some bias in the ADCs that read out each row. And just because the CCDs have only like one ADC or only one amplifier, like that's a few less sources of noise. Yeah.
And then you have your Poisson noise, which is like the square root of one photon. So,
yes. Yeah.
All right. Question over here.
Hi, amazing talk. And I have a question on slide 32, so the next slide.
Yep.
So you get the spectrum of like one source. So what are the other sources that are here? That seems like some specs. Is that like other X-ray sources?
Yeah. So these are when we shined our Manson source at this screen, at this detector, right? And then we integrate over all of these pixels. This x-axis, this color bar here should be a little bit bigger. That's like a data number. So that's like the count that we're getting out of the detector. And when we sum over all of the data numbers in this region, that's what we're plotting on the histogram here. Does that answer your question?
I had a question about like there's like other dots along the like those other sources. Are those from the same source? Or?
Those are from the same source.
Oh, okay.
Yeah.
So do you like also take data from those sources too, or just from one pixel?
This is just a titanium source. So this would be like if we had like, I don't know what that lamp is made out of, but if we like took a picture of that lamp and saw all the photons coming in, like it's a single source. We're just getting multiple different events from that source.
Oh, okay.
Yeah.
Thank you so much.
Yeah.
All right, we have an online question from Jackson Scheel. Wondering what the advantage of a beryllium filter is. And I'm wondering that too, because beryllium's like one of those no-no chemicals you never be around ever.
So the beryllium window, that was to filter out some of the lower, Chris, you might have to fact check me on this. That was to filter out some of the higher energy, lower, and it was to filter out some of the, filter out some of the lower energy X-rays. Yeah, Chris, can you help me a little bit?
It's like a game of charades.
Yes, okay, so it serves the same purpose as the Manson filters then, right? Like it filters out the, okay.
Want to bail him out, Chris?
Our light source, which is electron impact, it generates a continuum, visible light, ultraviolet light, primarily X-rays. We are concerned with measuring the X-rays with our X-ray camera, so we need to cut out or attenuate all the visible light and ultraviolet light, and that's what the beryllium window does. Intrinsically, beryllium absorbs and reflects the visible and ultraviolet light and transmits the high-energy X-rays.
Cool. Thank you, Chris.
All right. Let's go with Leiyla.
I'm really glad your presentation was before mine because I talk about CCDs in my own experiments. I wanted to know how long did you run your experiment for to get those counts for your CCD camera?
For a CCD camera?
Yeah, how long did it take to get those pixels?
I can't talk about CCDs because I didn't directly work with them. This titanium series that I analyzed here, this was 100 frames at 0.1 second exposures each. So the whole exposure was only 10 seconds.
Okay.
Yeah.
Okay, wow. Okay.
Question over here.
So I know that given that you are in the solar program, one of the main focuses of this science right now is to ensure that we're not oversaturating solar observations of X-rays. Is there anything else, astrophysically speaking or otherwise, on Earth that could benefit from being able to not be overexposed in the X-ray using this kind of technology?
Oh, that's a great question. Not that I immediately can think of. I know, I don't know if there's anything near, like the problem that we're having here, and it's actually only really a problem in the X-rays right now because they've solved it in the extreme ultraviolet range and like the ultraviolet range. The problem is just that these particular events are just so bright in the X-rays that CCDs can't handle them. I can't think of off the top of my head any sources of X-rays that are so bright that like they wouldn't be able to be handled by CCDs. Good question.
All right, J-Sub has a follow-up here.
Just to answer your question, you can think of we are increasing the dynamic range, not just covering the bright source. There are a very bright source in the astrophysics, but obviously much fainter than sun. But as we push the technology, we are bringing more powerful meters to collect more light to see faint sources. But when you do that, your detector now become very sensitive as well because you are collecting more lights. In that case, if you're using traditional detectors, you will be very limited dynamic range. But if you have sensors like this, then you can still keep the wide dynamic range from the bright source to the faint source at the same time. So that's one of the advantage. And then in any space missions, one of the key things is Torsren mentioned briefly is the radiation tolerance. And since we don't have to transfer charges like CCD, this is intrinsically much more tolerant, radiation tolerant. So it has a lot of application in space. So.
All right, and that's all the time we have for questions. Sorry, Leah. All right.
I'll talk to you later.
Yeah, private correspondence.
Cool. Thank you, guys.
Hello, does this work? I can't hear myself. Hello? A little bit.
The mouse is going to go off the screen and then onto that screen.
Maybe. Is that better? Yes, no? I can also project if needed, so. Okay. And I just click this here and.
Yeah, you can use this, use the mouse, you can use the clicker. You got a lot of options.
Oh, cool, awesome. All right, hello everybody. Oh, sorry, go ahead.
Gotta introduce you, jumping the gun. All right. For those of you clamoring for more of the Brent family, we have the younger Brent sister. So this is Leiyla Brent. And she's going to talk about the EBIT instrument that we have over in our labs at CDP. So go for it, Leiyla. Oh yeah, and she's coming from Loyola University, Maryland.
Hello all, thank you for coming to my talk. My name is Leiyla Brent. I've been working this summer with Dr. Amy Gall and Dr. Adam Foster. Our project is about improving the precision of a crystal spectrometer here at the SAO that we use to do X-ray spectroscopy to decode the sun. So in this presentation, I'll go over our science motivations, how that applies to solar physics, our experimental setup, what I did for my project, and then the conclusion and future work. So high energy environments across the universe emit a plethora of X-rays that can tell us about their physical conditions and the dynamics and what's going on inside of them. However, interpreting X-ray spectra depends on atomic models that often lack the precision to understand what exactly is going on. So we need to close this gap by improving the accuracy of atomic data through lab-based measurements here. So how can we use this to look at the sun? So we can study the sun with X-ray spectroscopy to help us characterize the most extreme behavior of the sun and what process may be behind open problems like the coronal heating problem. So when we get spectra from the sun, we can see what these lines look like in their line profiles to get the following parameters like chemical abundance, turbulence, plasma density, and ion temperature. So how exactly do we measure this in a lab-based setting to a high precision? We use a technique called crystal X-ray spectroscopy that utilizes the lattice spacing of a crystal to diffract X-rays and to study their wavelengths and energies very precisely. So how do we do this? So this is our experimental setup. We inject the atoms into the electron beam ion trap with the MEVA and the gas injection system, and then we look at those X-rays with the crystal spectrometer. So let's look at this really closely. So what is the MEVA? This is a metal vapor vacuum arc. This uses a high voltage arc between an electrode and a metallic sample inside the MEVA to produce and inject ions into the trap. These are floated into the EBIT. This is the electron beam ion trap. This uses an electron gun to bombard these ions with more electrons to create, trap, and study highly charged ions. These X-rays are then floated into the crystal spectrometer. They go through a slit, they're directed, they hit the crystal, and then they go into the CCD detector. This has a resolution about 1.4 eV, and the CCD detector captures these diffracted X-rays, and it measures their intensity as a measure of counts versus pixels. So we can use different crystals for the crystal spectrometer. They're housed right in the middle there, as kind of when it goes back up, that's where they're housed. And we can put different crystals in there to measure different energy ranges for our studies. So before I get into my project, I would like to explain the basis for it. The CCD detector can only see a narrow energy range, so we need to rotate the detector so we can see the full range of X-ray energies. Say our crystal spectrometer is like a prism that can only see small regions of the rainbow, we would have to rotate it to see the entire rainbow. So how can we do this and measure how we're moving precisely? That is the basis of my project, and that included installing a linear encoder and a laser encoder. And to automate the way we move the spectrometer, I had also added a motor, and this was all towards the goal of creating a calibration curve for the instrument. So what did that include? So first things first, what is a laser encoder? This is a sensor that measures distance by bouncing a laser off a surface. and calculating the distance based on the angle of reflection. So in our setup, as the spectrometer moves, the way the laser hits the certain metal part, and it gets closer and closer and closer to the laser as the spectrometer moves. From currently it's in 63 degrees, so as it moves that way, it'll get closer and closer, and we would see that on the software that comes with the laser sensor. Unfortunately, with the software, we kept seeing a 0.06 millimeter peak-to-peak flickering in our measurements, which we thought were from vibrations on the EBIT. After what we thought were improvements, we still saw the flickering. We had to switch over to primarily using the laser encoder for these measurements. So what did that entail? So what is the linear encoder? This uses a measurement head, seeing this kind of the rectangular thing on the rod right there, that has a 5 micron resolution that tracks the position along a rod. This allows us to look at how the spectrometer is moving really precisely, even better than the laser encoder. And its display, pictured below here, uses a serial to USB connection that allows us to send these measurements to the computer. So as our spectrometer moves, this goes from bottom to top as we move it, and we can see this really clearly on the display and now on the computer. So the bulk of my project focused on creating these serial to USB cords for the computer, thanks to Dr. Jenna Samra, who had a plethora of these DB9 things that we could connect the wires to. These were able to be made, and I could connect it to the computer, and I also made a Python script to read out these encoder measurements with Python. So I was really excited with this at first and decided, oh, let's create a relationship between the Bragg angle that for our crystal spectrometer and the linear encoder measurements. And this took 2.5 hours to kind of turn the gear very slowly. But we ran into a big problem. To zero the display for the linear encoder, I had to use a caliper to kind of zero it and put in like, oh, this is where the zero spot is. This is where we're going to stop. You can't do that because, as you can see, this is actually a very linear relationship. But I had to do a quadratic fit for this because my use of the caliper introduced human error into the measurements. So I decided, don't do that ever again. Our improvements that we made, though, is that the rod for the linear encoder needed to be changed because it was preventing this crystal spectrometer from moving all the way. So we bought a smaller one that introduced a physical limit, so I no longer have to use this. So as I said, it took 2.5 hours to turn a gear to move the crystal spectrometer from 63 degrees to 25 degrees. So that means we have to add a motor to speed this process up. So there was already a motor there, but it was really old. It was missing the green terminal connector for the transmit, receive, and ground pins. The gear and coupler connected to the motor was non-existent, and also the coupler on there was way too bendy to even connect to a rod to turn and rotate the crystal spectrometer, and there was also no way to communicate to both the motor and the linear encoder at the same time. So I created a kind of a DIY pins for these ports and to test sending commands from Python. Later on, a pluggable green terminal was ordered, and it was plugged into the motor for a more permanent position. And then I also made a Python GUI using the libraries PySerial and PyQt6 to communicate with the motor and send movement commands. So you can see in the top, those are the different types of commands that we would see. And read the acknowledge characters that I would get back from the motors, which you can see here at the bottom. It used the serial command language made by the Applied Motions product company. So that was really good. They had a 600-page handbook of all the 600 different commands they all had. So that was really cool to look over. So we did take some measurements with the crystal spectrometer. We have a calibration source, fluorescent source that sends X-rays to the CCD. And like Tos's project, we also tried to look at some pixels. But unfortunately for mine, it wasn't very unfruitful, so we hope to take more measurements in the future. So the challenges that I had was that the linear encoder and the laser encoder, they have very different industry applications. So I made 15 different calls to different companies over the course of the summer. Their customer service people are very nice and very understanding, so that was really nice. I also had to understand the limitations of the encoder. That included finding out that the laser encoder didn't work as well as we wanted it to. I also almost damaged the motor during setup by hot plugging it. I didn't know that was very important. Also, I was working with really old cords that Microsoft couldn't identify the USB drivers for them. And also, I had to wait on part deliveries like the rod and other things as well. Also, the bearing broke on the crystal spectrometer. I couldn't move it for a week, but it was okay. It got fixed. So, yes. So, conclusion of future work, the additions made to the crystal spectrometer now allow easier use and will help towards creating a global calibration curve for all crystal types in the chart, using a relationship between the linear encoder position, the motor steps, and the Bragg angle. Although our first measurement with the spectrometer this summer was unfruitful, more measurements will be made, and hopefully we can put the crystal spectrometer back on the EBIT, and I hope to make more updates to the GUI's design. These are my citations. And I would like to give a special thanks to my mentors, the people who were around to help me in the lab, and the rest of the engineers at the CDP, and Chad and Kathy for being amazing. Thank you.
You guys are absolutely just screaming through these talks. All right, we got quite a bit of time here for question and answer. So, Jenna.
Thanks, nice talk. I had a question about your linear, or your calibration curve, I think, that you were trying to make, if you could go back to that slide.
Yes.
To me, it looked like it was pretty linear, despite your human error. Why did you have to use could you maybe discuss that graph a little bit more, and then tell me why you had to use a quadratic to fit that?
I wish I could zoom in, but if you see at the top left, there's kind of a bit of a curve there, and that was from me zeroing it with the caliper. I tried to do a ton of measurements. I think I did like 50 measurements, averaged it out, and said, oh, this is the zero for the linear encoder. That obviously did not work as well as I thought it was going to work. So yeah, I had to actually do a quadratic fit with a total linear relationship. So I really didn't, I had to just throw it out.
So you expect a linear relationship here, and
yeah.
it's not. Okay, I gotcha, thanks.
Over here.
You had a list of all the different crystals that you could use. I was just curious if you could explain more about that chart, and also exactly which crystal you actually ended up using for the experiment.
Oh, so the crystal in our experiment, we used the silicon 111. You see it's the third one there. So discussing more about this, so the numbers you see, the parentheses refer to it's the Miller indices. This just refers to if it's hexagonal planes inside the crystal lattice, or if they're cubic planes inside the crystal lattice. And that really won't tell you exactly about it doesn't really relate too much to the energy range. Actually, the spacing in the lattice structure relates to the energy range. So does that answer your question? Okay.
Over here.
Hi, amazing talk, and I had just a question. I don't know if it's relevant or not, but do you have any plans of making a database using the tools that you created with the crystal spectrometer?
What do you mean?
Like a database of different crystals or chemicals using the spectrometer.
Oh yeah, I hope to add it to the GUI because since the different crystals have different energies, when I create the calibration curve, they need to be different to apply to each crystal.
Oh, awesome! That's good. Thank you so much.
Got Chris?
In an ideal world where you were able to take data, how long would it have taken you to populate this entire spectral range with the crystals that you wanted to use?
Oh wow. So let me explain something really quickly. So it took 1 hour to get nothing from this NC-no structure. So we would have to run this for a very long time. I'm guessing maybe like 6 hours per, just to get the counts we need to actually see some structure very well. So hopefully that will add to the calculations. If we were to test each crystal and track one line, that would take probably a couple more weeks to do that.
So almost the entire summer.
Yeah.
So we'll go with Randall and then Torsren.
You mentioned the flickering in the laser encoder. Did you ever figure out what was causing the flickering if it wasn't the EBIT?
So I did call the company to see what may be causing that. Apparently, you're not supposed to shine it at reflective surfaces. That's the entire point. And they told me cover it with some dark tape. We also tried to do that, it didn't work.
You exposed this to light? How could you?
So I really didn't understand what they meant there, and we thought it could be the vibrations or the temperature within the lab that was causing some measurement things, and everything we tried, we just kept seeing it. So, yeah.
Torsren?
I'll ask you the same question that you asked me. What was for the CCD image that we saw at the very back, what was the exposure and or how long did it take to get the exposure? Yeah, that one.
So this one specifically, I remember it was for 1 hour. It's like 15-minute acquisition times to get each kind of slice of it. So yeah, it took about an hour to get this, to get nothing. So of course that means we need to take a little more time with these measurements to get the counts we need. Yeah.
That's a shame. Oh well, cool.
Okay.
Great talk. I am a little lost on the plot on the right-hand side. Could you just explain that one more time? The white lines, just what they're representing.
Yes. So this is dead lines. We can't see anything there. So it's just light.
Okay.
We can't see pixels anymore. So it's just there.
Okay. Is it spatial? Like, is it like this is a picture of something that?
Oh no, they're just there. They're in every single image, no matter how you turn the CCD. It's just, yeah.
It's
Okay.
a photograph.
Yeah.
Okay. Thank you.
Yep.
Any more questions? Going once? Going back? Chris is going.
So 2 questions. What was the main lesson you took away with your experience this summer? Number 1. Number 2, what was the funnest thing that you did this summer?
The funnest thing that, I'll start with the second question. The funnest thing that I did this summer was seeing things work after a very long struggle. So that was very rewarding. What was the first question? I forgot.
What's the main thing you learned?
The main thing I learned? Stuff takes time. I did not think this would take this long, and I did not foresee the many mistakes that I would make and how stuff just didn't work out. So it was really, I guess that fits into the kind of second answer, that it was really rewarding to see stuff work after I worked on it. Yeah.
Have you spoken to Dr. Gall about how long she's been working on it?
A little bit, yes. She's been working on it for a long time.
Anything else? Going once? Going twice?
Oh, before the
Oh, we have a quick
Before
comment?
the end of my talk, actually, there's another talk at lunch by Dr. Julio Dizana
Oh, he
from
beat me to it.
Cambridge, who's going to talk about X-ray spectroscopy a little more. So if you want to check that out and get a follow-up, go ahead.
All right. Thank you so much for announcing that. So, and with that, we're going to go to an early lunch. So we have an extended lunch. It's going to go all the way until 1:30. That's so we can give you guys time to actually go and see Julio's talk down in the lower library space. So please go ahead and see that. So, and with that, let's give Leiyla one more round of applause. Please eat our food and come back at 1:30.
the lift, what would you think?
Right side.
All
Turn
right.
this way, make sure your ear doesn't hit it. Good. Otherwise,
That's
you'll
clear.
hear nothing. Welcome back, everybody. Hope we had a productive lunch. So, as we enter our afternoon session here, we're going to be going through the last 3 talks in the symposium. So the next talk is going to kind of round out our kind of mini-series here on instrumentation. So we have Nick Smith. So he just graduated with his associates from the Maricopa County Community College District. So, and he's transferring to University of Arizona to pursue his bachelor's career. And he will be talking to us about ACEs. So go for it.
All right, so my name is Nick Smith, and I've been working on developing and characterizing the Airborn Coronal Emission Surveyor, ASUS 2.0. My mentors were Dr. Gina Samra, Dr. Chad Madsen, and Lucas Giuliano. So, one of the reasons that we want to survey the corona is because coronal heating is not well understood. If you look at the graph on the left, which displays the temperature in Kelvin versus height above the convection zone in kilometers, we can see that as you get farther away from the sun, it gets hotter for some reason. And there's a lot of people who would like to figure out why. Specifically in the corona, the temperatures increase to millions of Kelvin. And so it's thought that magnetism is going to play a role in this because the sun's magnetic field is very good at storing energy and then releasing it suddenly in magnetic reconnection events. But right now, the instruments that measure the corona, they typically do so in shorter wavelengths, which can make measuring the magnetic field problematic. So what ASUS wants to do is survey the infrared spectrum of the corona, which infrared light will have the longer wavelengths, to find candidates for a future instrument to measure something called the Zeeman effect, which can tell us the magnetic field. So the Zeeman effect, as pictured on that middle image there, will cause an atom to have its emission split into multiple spectral lines in the presence of a magnetic field, and the degree to which that splitting occurs is proportional to the magnetic field strength. And so what ASUS wants to do is get a spectrum such as this one on the right, which is a theoretical model of the infrared corona, so that we can find good candidates for a future instrument to measure the magnetic field of the corona. So there was a previous attempt at doing this called AirSpec, which was a slit spectrometer. You can see an image of the AirSpec spectrometer on the left there. What it did is it used a grating to diffract the light and then send that light to a detector to obtain the spectrum. However, when you do that, you're going to have to trade off between either your spectral resolution or your passband. And in the case of AirSpec, the spectral resolution and passbands were not quite what was desired. And we can see a comparison of the AirSpec and ASUS passbands on this image to the right. The top row shows the 4 AirSpec passband ranges. The green line in the middle shows the current ASUS passband, whereas the blue line at the bottom shows what we want the ASUS passband to be in the future. And the reason the ASUS is doing better with the passbands is something called Fourier transform spectroscopy. So if you look at the image on the left, specifically the lower part of the image over here, you'll see something called a Michelson interferometer. How this works is the light comes into this beam splitter here and gets split along these 2 paths into these corner cubes, which are reflective surfaces. One of the corner cubes will remain stationary while the other oscillates back and forth. Vic, are you using your cursor? Yeah. Oh, can you not see it? Oh, okay. So the beam splitter, or I'm sorry, the corner cube on the left, which you can see.
Yeah, 1 second. Is it possible it's extending? Yeah. So it's still extended from Leiyla's talk, so it should be on there now. It'll go off this side and it'll wind back up onto here.
Okay, got it.
Perfect.
All right. The passband, it's the range at which you are measuring the spectrum. So if there's any lines outside your passband, you won't see them. You'll only see lines within your passband. All right, so this Michelson interferometer, light comes down here into the beam splitter, splits it along this path and this path. This is a reflective surface called a corner cube. That one will remain stationary. This one will oscillate back and forth.
that oscillation will give an interference pattern when those beams recombine in the beam splitter to get sent back to the camera. We call that interference pattern the interferogram, and the Fourier transform of that will give us a spectrum that we can then measure. And so the benefits of this is that the resolution is going to be limited by the amount we move that moving corner cube down here, whereas the passband is limited by the camera's wavelength range, so we don't have to have that trade-off like we do with the slit spectrometer. All right, so now that we know how the Fourier transform spectroscopy works, and again, that Michelson interferometer is going to be down here in the image, I can show you how the rest of ASUS works. This picture here on the left is just a picture of ASUS 2.0, whereas on the right here we have a block diagram of the same instrument that's maybe a little clearer because we don't have all these wires here. So what happens is light from the sun gets reflected off of this mirror into our telescope, which then reflects the light into the interferometer, where we get our measurement. And so the airborne coronal emission surveyor needs to be airborne because the atmosphere of Earth is very good at absorbing infrared light. So we want to get above all of that light so that we can actually see the coronal emission instead of just a bunch of atmospheric absorption. We want to do this at infrared wavelengths because they're longer, and therefore the Zeeman effect will be more pronounced. And we also have to do this during an eclipse, or else the light from the photosphere will drown out all the light from the corona, and we won't be able to get a coronal measurement. So we actually have to take this plane into the air and follow the path of totality of the eclipse in order to get this measurement. All right, so the previous version of ASUS had a few problems as well. For one, the camera broke. You can see the replacement camera there on the left that was used in the 2024 flight of ASUS, and a model of the ideal camera is just to the right of that. The spectral resolution needed to be improved. There was some shaking in the plane that messed with how we measure the optical path difference. And we needed better sensitivity due to some aberrations in the optics that introduced some wavefront errors and made it difficult for us to get a good spectrum. This image on the right here, this is showing an image from 2024. That red circle there is sort of how we step down the aperture. We needed to do that to reduce the wavefront errors to actually get any spectrum at all, but the goal is to increase the usable aperture so that we can get a better spectrum. All right, so to improve ASUS from the previous version, we're going to need to change out those optical components and make them better. We're going to need to test those components in the lab to make sure they're actually improving things. We're going to do a ground-based solar observation to help with calibration, and I'll explain that later. And then we're going to analyze the performance of everything to see where the instrument is currently at. All right. So as far as lab testing goes, we do most of our lab testing with lasers because they're a very well-known source. They're monochromatic, so they only emit at one wave number. And so in the lab, one of the things we tried to do is measure the transmission of the solar filter that we used during our solar observation. Unfortunately, we did not quite have the right tools for that, and so we need to send that out to another lab to get it fully characterized. We also started changing out the optical components. Mainly, this beam splitter down here was the main priority. In the 2024 flight, the surface of the beam splitter had some imperfections to it, which were causing wavefront errors in the camera and making the spectrum difficult to measure. We also changed out all these other components that are marked in red. Those we don't believe had a great impact on what was happening now. And then we also, in the lab, improved and documented the alignment procedure. All right. So for our solar observation, you can see our setup out here. This is the ASUS instrument itself, and this right here is just the computers that we use to control the instrument. So we're doing this on the ground rather than in the sky because for testing the instrument, we actually want to see some atmospheric absorption because the atmospheric absorption lines are very well known, and there's a lot of them, which helps for calibrating our wave number axis so that we actually know in the future what lines we're going to be looking at. And the sun is also a very well-known source. The photosphere of the sun is a well-known source. And so we can use that for radiometric calibrations as well. And in making this observation, we had to make a couple considerations. You'll see the shielding over the instrument here. That's to keep stray light from the sun out of the interferometer and smearing out our signal. And then there's also, unfortunately, these things called clouds, which sometimes just block out the sun entirely, and we can't use that data in our observation. What we want to see is this, a nice clear sun with a very small sunspot there that you might be able to just barely make out. And so what did we learn from the solar observation? Well, we can look at the interferograms from ASUS 1.0 in 2024 here. It's the interferograms we got during our solar observation. And we can tell that the interferograms are larger, which suggests an improvement to the sensitivity. So in ASUS 1.0 here, we only used a 1-inch aperture. We got a pretty small interferogram. ASUS 2.0 with a 2-inch aperture and the improved optics, much larger interferogram, which means we're getting a lot more signal. And we see here with the 6-inch aperture, the size of the interferogram actually decreases again, which suggests to us that there's still some more optics that need to be changed out and improved upon in the future, but it's still an improvement over the 1.0 version of ASUS. All right, and so now looking at the wave number calibrations, we can see, if we look at this graph on the left here, in blue we have a theoretical spectrum of the atmospheric absorption that we got from NASA's Planetary Spectrum Generator. In the orange, we have some uncalibrated ASUS data. And since it's uncalibrated, we just have some arbitrary units on the y-axis and wave number in inverse centimeters on the x-axis. And we can see, especially a good example is these two lines right here, that they're shifted off from each other a little bit. And so that makes it difficult to tell which lines we're actually looking at. It would be possible to claim one line is something when it's really something else. Uncalibrated, the shift is about 2 wave numbers away from what it actually is. After calibrating it, we can get that difference to only about 0.05 inverse centimeters, which is a much better measurement. And so this calibrated image on the right is going to show, again, in blue, that theoretical NASA spectrum versus in orange, the calibrated ASUS data, with the units on the y-axis being photons per second, per steradian, per meter squared, per inverse centimeter, and wave number on the x-axis. But we can see the calibration works well, and we can actually tell which spectral lines that we are looking at. All right. Now, for radiometric calibration, we need to know the absolute line intensity that we're measuring. As you can see with the graph on the left, where's my thing? With the graph on the left, again, we're comparing the theoretical NASA spectrum in blue to uncalibrated ASUS data in orange. Now we can see that they're not lining up yet because they're not calibrated. You might notice that there's a slope to the uncalibrated data. We believe that is due to our solar filter. We believe that filter is attenuating the higher wave numbers more so than the lower one. And so if we look at this curve up here, this curve represents how our instrument is actually changing the spectrum we get into the spectrum we get from the sky into the spectrum that we measure out of ASUS. And so if we take the inverse of this curve, we can then multiply that by the uncalibrated ASUS data to get a calibrated spectrum, as seen here in orange. Again, with photons per second, per steradian, per meter squared, per inverse centimeter on the y-axis, and a wave number on the x. And we can see that we actually have a much better fit. And now that we have a method of getting the absolute line intensities, we can measure, if we were to make a coronal observation, we can measure how the intensity changes with radius. We can validate various atomic physics models. We can use line ratios to measure temperature and density, and maybe find the strongest lines for use by future magnetometers. Another thing that we tried to measure in the lab is the instrument line shape. So this tells us our spectral resolution by examining how much our instrument is going to broaden a given line. So we use our lasers in the lab to test this. We shoot the laser into the instrument, and if we look at this graph on the bottom left, we'll see the blue curve is the actual data recorded by ASUS, the actual spectrum recorded by ASUS. And the orange line is a Lorentzian best curve fit to that data. We use that curve fit to get the full width half maximum, which is a measure of our instrument's resolution. At this particular wave number, the full width half maximum, the resolution, is about 0.3 inverse centimeters. The ideal full width half maximum, the best our instrument can really achieve, is about 0.24 inverse centimeters, so we're really getting close to the best case. And this is definitely an improvement over AirSpec, whose full width half maximum at a wave number of 7,000 inverse centimeters was 2.5 inverse centimeters. So we're getting close, like 10 times improvement. Now, that full width half maximum in resolution is going to change based on which wave number we're looking at. We can see this on the bottom right graph, which compares the full width half maximum on the y-axis against wave number. And we can see that there is a change with wave number to our resolution. There is a problem with measuring the instrument line shape and resolution in the lab. We can examine that on this top graph here, where the red line represents the wave number ranges in which we do not have the lab equipment to measure the resolution, versus in blue is the current ASUS camera range. So that is an area that needs to be explored, and yeah, it just needs to be explored and fully characterized. All right, so as for the current status of ASUS 2.0, the average spectral resolution that we've been able to measure is about 0.3 inverse centimeters, which is about 8 times better than AirSpec was at the 7,000 inverse centimeter mark. And again, our best case is 0.24, so we're getting close to that. Just as another explanation of instrument line shape and resolution, if we look at the graphs on the top, we can see an example of the ASUS instrument line shape on the left, and we can compare it to how much narrower it is than the natural line profile of a silicon tin ion, which is in that middle section. And we can consider an emission line such as that one to be resolved when our instrument line shape is narrower than the natural line profile. And then just to the right of that, we have another comparison between AirSpec and ASUS. AirSpec is in orange, ASUS is in blue, and it's showing us how the ASUS instrument was artificially broadening the lines more so than ASUS is. As far as our passband is concerned, our current spectral range is from 6,000 to 10,000 inverse centimeters, which is a far larger passband than AirSpec was, but ideally we want to get to a spectral range of 2,500 to 10,000 inverse centimeters, but for that we're going to need a new camera. As far as sensitivity is concerned, we were able to reduce those aberrations on some of our optics, namely the beam splitter, and actually be able to get some usable data from the full 6-inch aperture. Although we think we can improve that in the future, we think improving the corner cubes will better increase that sensitivity. Unfortunately, that exact improvement will be unknown until our solar filter can be fully characterized by another lab, because we unfortunately do not have the equipment to fully do that ourselves. We also have some artifacts in our scans right now. We can see that in the graph on the bottom. And when I say artifacts and scans, each scan is an oscillation of that moving mirror. So whenever we oscillate that mirror, if we put a laser into it, we'll see that emission line. Is it not going to come back? Nope. OK. Well, we see that tall line is an emission line from the laser. That's what we expect to see. And then off to either side of that, we have some random stuff that we need to find out how to eliminate, which most likely has to do with our motor. And to finish off the stats of ASUS 2.0, we also have a better alignment. As far as future improvements are concerned, we can finish off measuring the instrument line shape with a white light measurement. We need to characterize the noise of the instrument to get a signal-to-noise ratio, add cryogenic cooling and a new camera to expand that passband, finish upgrading the optics, characterize that solar filter, mitigate the scan errors, and then finally fly it during an eclipse to measure the coronal infrared emission. That's it.
Questions? Over here.
Hi, Nick. That was an amazing talk. And I had a question about the previous slide, the one with the the one before that, yes. So we have like the chart with the laser spectrum with artifacts. So can you go over again, like what are those like small artifacts at around 7,000 and 9,000 wave numbers?
Yeah, we believe those are probably errors created by our motor as it scans that mirror back and forth. It's not going to be moving perfectly smooth, and that extra stuff is probably what's introducing those errors. Earlier in the summer, those errors were actually larger. We realized that our motor was set to a setting that it wasn't supposed to be, and as soon as we switched that setting, the errors got down to where you see them now. And so since that's what reduced the initial errors, we believe that's still a motor problem that we need to fully figure out later.
Torsten.
Thank you for the talk. I'm happy to contribute those 12 screws. I wasn't sure what OPD meant on one of the first couple slides. What does that stand for?
OPD is the optical path difference. So if we go back to the Michelson here, please tell me.
Okay, so that's just the
Right,
corner
so
cube going for.
Right, it's the difference between this path and this path.
I see.
And that's what gives us the interference pattern that we then measure.
Okay. I have one other question, which is what's the holdup with, so on the instrument line shape slide, you had some data points. I was wondering what the, yeah, that one. I was wondering what the holdup was with not being able to get the other ones. Is it like you can't get a laser of those wavelengths or?
Yeah, just the lasers we have in the lab can't extend the entire wave number range of our camera.
Okay,
So it's just something we can't do quite yet.
Cool. Thank you very much.
All right, let's go with Steve.
The instrumental profile for an FTS should be a sync function. So I'm wondering why you're using a Lorentzian, or why I don't see sync wiggles and things.
We were just looking for the full width at half maximum, so I think that's why we went just for Lorentzian instead of the full sync.
Can I follow up on that?
Sure.
Yeah, that's a good question. We would expect to see a sync. The Lorentzian, as Nick said, was just a way to get the full width half max because that empirically looks like a Lorentzian. The sync, actually the sync turns out to be that when you sample the sync, you're sampling it at the zeros. If you have a perfect system and you run through the math. So you actually, I believe you would expect, we could maybe talk offline, but I believe you would end up with something of this shape because of where you're sampling the sync function. So you don't get the dips that go negative, if that makes sense. You would have to kind of oversample the spectrum. I think there are some measurement issues with the way that we measured this that makes it look that way, is essentially what I'm saying. Yeah, they're probably blurring it out, and there's noise in here. So I think all of that meant that we just went with the Lorentzian because that's what the data looked like.
Probably have time for one more question. Chris.
Can you go back to your calibration slide?
Radiometric or wave number?
We can start with this one.
Okay. That's a good sign.
Can you explain how you get to the right again? So you
How
have
I go from the left to the right?
left to the right, yeah.
Right, so we fit a polynomial that will pretty much map the uncalibrated points to the theoretical points. So we're trying to line up the peak of each dip to each other using the polynomial.
This is in wave number space, right?
Sorry, what was that?
Wave number space, you're
Yes.
filling a polynomial. So how do you fix the amplitude? Because now you're in photons per steradian per second.
Right, so this image on the right is the fully calibrated with both wave number and radiometric calibration. To get that radiometric side, we take the inverse of that curve that you see on the top, because that curve represents how ASUS will change input data to the output data.
Yep, so how do you get that curve in the top right? You mentioned something about the filter response as a function of wave number or wavelength. How do you know that? Or is this just from taking a ratio, or how are you getting this?
Right, so we think that the filter is attenuating the higher frequencies more, because those frequencies are going to be closer to the peak of like the black body curve of the sun, and so they would need to be attenuated more. I'm sorry, what was the second part to that question? Oh, it was
Maybe
how
a-
we got the curve itself.
It may be a general question. How do you know that it's attenuating more at some wavelengths versus others? Did the manufacturer did not provide a curve or anything? A response curve?
No, we for the filter, we didn't have that information. But we can just compare the spectrums in a code and just find a polynomial fit between the two.
So you just
sets.
scale.
Yes,
Yeah.
so he fit that polynomial, and we believe that the shape of it is due to the slope of the filter, like you said, because that would make sense for that filter, but we don't have measured data on it. Yeah. But we are going to get it from a fellow collaborator.
All right, and that's all the time we have for questions. So let's give another round of applause for Nick. Nailed it. Okay. Can you get the live mic on? Okay. Try to put this in your pocket in case you accidentally run off with it. All right. Up next, we have Savannah Rudzinski. So she's coming to us from Wheaton College. That is the one in southern Massachusetts, not the small seminary in Illinois that has the exact same name. So she's going to be talking to us. This is kind of a bit more of an out there topic. She's going to talk to us about what flows on the sun can teach us about finding exoplanets. So take it away, Savannah.
Thank you. Hi, I'm Savannah, and today I'll be telling you a bit about how we can use our own star, the sun, to improve our detection of exoplanets. So, one of my main interests is the search for life beyond Earth, and one of the ways we go about finding life is by looking for exoplanets, or planets that orbit other stars. One method that we use to detect exoplanets is called the radial velocity method. When an exoplanet orbits a star, it exerts a small gravitational pull on that star. This causes the star to wobble in our line of sight, which we can detect from Earth. Because of the Doppler effect, when the star moves toward or away from us, we see a shift in its spectrum. Okay. As you can see from this observer's view, when the planet is on the left side of its orbit, it pulls the star slightly away from us. Due to the Doppler effect, this causes a redshift in the star's observed spectrum. When the planet moves to the right side, it pulls the star slightly towards us, causing a blue shift in the spectrum. By observing these shifts over time, we can not only detect that an exoplanet is there with the stellar Doppler shift, but also estimate its mass. However, currently our radial velocity measurements contain an unknown noise source, which is making it difficult to detect smaller Earth-like planets. As you can see on the left, the masses of the exoplanets we've been finding since around 2010 have leveled out to about the mass of Earth. We can also look at a plot of the radial velocity semi-amplitude, or how much the host star of a discovered exoplanet wobbles over time. This semi-amplitude here. And that has also leveled out to about 1 meter per second. We have found some planets close to Earth mass orbiting small stars, but we have not yet found any planets of the mass of Earth orbiting a sun-like star. When a planet is smaller or farther away from its host star, it has less of a gravitational pull on its star and therefore a lower RV semi-amplitude. This makes it more challenging to detect those exoplanets using the RV method,
when there is background noise. In order to detect smaller exoplanets, we want to improve RV measurement precision from about 1 meter per second to 10 centimeters per second by identifying noise sources and accounting for their radial velocity signals. And 10 centimeters per second represents finding a planet with the mass of Earth at 1 AU from its host star. I will talk more about this later, but here's a visual of the noise in the Doppler shifts that we are looking at. We want to be able to detect the radial velocity signals of planets that are hiding in this stellar noise. But we actually do know that this noise is coming from magnetic features on host stars themselves. A star's surface isn't uniform. It has brighter and darker spots on its surface, which affect radial velocity measurements. But before I talk about why that happens, here's some background on some important features on the stars. We call most of the sun's surface quiet sun, which is made up of convective cells, where hot plasma rises and cool plasma sinks. Sunspots are areas where the magnetic fields are so strong that they inhibit convection, preventing plasma from heating and creating cool dark spots. The darkest part in the center is called the umbra, which has the strongest and most vertical magnetic fields. Surrounding the umbra is the penumbra, which has a more inclined magnetic field. We also have bright areas called magnetic network and plage. Plage and network also inhibit convection, but not as much as sunspots do. So here's a video of convection cells in the quiet sun. In these regions, hot plasma rises to the surface and emits light that's blue shifted from the motion coming towards us. Since the upflowing areas are larger and brighter, they contribute more blue shifted light overall. However, in magnetically active regions, like sunspots, convection is suppressed. This is called suppression of convective blue shift. With less rising plasma, there's less blue shift, which not only affects the brightness or intensity, but this alters the measured velocities. So there are two main ways magnetic features affect radial velocity measurements. First, they change the intensity weighting, basically how much each part of the surface contributes to the velocity that we measure. Second, they alter the local velocities by reducing the convective blue shift where the magnetic field is strong. By studying how different magnetic features impact both intensity and velocity, and using the sun as our best observed example, we can improve our models of stellar radial velocities. This is important for the detection of smaller exoplanets, whose signals can be masked by noise from these features. The radial velocity signals of the quiet sun, umbra, penumbra, magnetic network, and plage of the sun have already been studied. So the goal of my project was to investigate radial velocity signals of less studied features called mote flows. So mote flows are outward magnetic flows from the penumbra of sunspots. They typically move at 0.5 to 1 kilometers per second. So here you can see sunspots, and what I'm looking at, the mote flows, are these outward flows coming from them. So in this project, I've augmented my mentor Michael Palumbo's code, which quantifies the RV signals of the quiet sun, the network, plage, umbra, and penumbra to quantify the radial velocity signals of mote flows. So Michael's code uses SDO observables like an intensitygram, a magnetogram, a Dopplergram to classify pixels from an image of the sun into some of the region types that I mentioned earlier. We can use the continuum intensity, magnetic field strength, and line of sight velocity values associated with pixels from the left, and an algorithm of various thresholds to identify the region type of each pixel. For example, first, sunspots can be separated from the rest of the features because they're much darker. Then, to separate bright features, if the magnetic field strength of a pixel is small, it's quiet sun, and if it's large, it's either plage or magnetic network. So the goal of my project was to figure out which pixels in an image belong to mote flows and quantify the RV signal and suppression of convective blue shift of mote flows, how different they are from the quiet sun, so that we can correct stellar radial velocity measurements for the signal when looking for exoplanets. So to identify which pixels are motes, I started with one timestamp in January of 2014. Since mote flows surround sunspots, I took the pixels that are already classified as sunspots, performed a binary dilation, expanding out to get pixels right outside the spot. Then I would remove the sunspot pixels from the center, average the values in that leftover ring of pixels, repeat the dilation process, and plot average velocity, magnetic field strength, and continuum intensity in each dilation ring to see if there was a steep drop-off in values that would define the end of a mote. There are different ways of finding the pixels bordering a region. For example, you can either include or exclude the corner pixels as you go out. This too is what it looks like to dilate without corners. With corners, more of the pixels would be shaded in here and make the two look boxier. So to preserve the shape of the sunspot in our simulated motes, my mentor, Steve Stark, calculated a relationship to alternate between those two to avoid ending up with square or diamond-shaped motes. These are the resulting plots of the average intensities, magnetic fields, and velocities for each ring of pixels, color-coded by the location on the sun. The x-axis is the number of binary dilations, and the y-axis is the average of a particular value in that ring of pixels. We know that the boundary for outside a mote depends on the area of the sunspot. So a bigger sunspot would have a bigger mote. So I marked the plots with an idealized average radius, which assumes that the spots are circular. You can see that as we move away from a sunspot, the brightness increases, the magnetic field strength decreases, and the line of sight velocity decreases. In these plots, I was looking for a clear sign of the point when we had expanded out too far and the pixels were no longer part of the mote, but it was unclear. I also plotted the same average values, but for one mote as it rotated across the sun, color-coded by spot location. In these plots, we noticed that the radial velocity curves of similar location and spot sizes have different amplitudes. So I marked motes left and right of the central meridian with an asterisk, and I will explore that topic again later. In these plots, there still wasn't a clear change in values that marked exactly where a mote ends. It's possible that we weren't seeing a clear transition because motes are not perfectly symmetrical, and we could have been mixing mote and non-mote pixels in our outer dilations, or because the velocity of the motes themselves decreased gradually. So we needed to observe physically what was happening to get a better idea of how far to dilate to the end of a mote without going too far. So we decided to pivot to observing the physical phenomena in HMI magnetogram movies, like the one that I showed you earlier. I observed movies from a few months in 2014, including the time frame in the previous plots, and compared those motes to the ones I would generate with the code. I would tweak how far to expand motes in the code by trying different constants times the idealized average radius, since motes are proportional to spot size, and I would compare them to what the motes look like in the movies. So on average, the end of a mote was around but slightly smaller than the idealized radius, about 0.97 times, but in areas of densely packed spots, we found that the motes didn't extend as far as those that were isolated. Through observation of several months in 2014, motes in complex regions only extended out to about 0.65 of the idealized radius. So we decided to implement these values into the code that performs the dilations, and then we finally had initial mote radii to select mote pixels. So going back to the code, this is what the region classification images looked like after adding motes and reclassifying the other pixels. Motes are added on the right figure in green. You can see that some plage has now been reclassified as mote. Once we identified the region types of the pixels, we could classify, or we could calculate the total velocities and the suppression of convective blue shift for each region type for each mu bin, with 1 being the center of the sun and 0 being the limb of the sun. At disk center, we are observing vertical motions from the feature, and near the limb, we're observing horizontal motions from the feature. These first plots show data from all of 2014. On the left column, we have the center to limb trends in total velocity for each region type, and on the right column, the trends in suppression of convective blue shift. Just as a reminder, suppression of convective blue shift is how different the total velocity of a region type is from that of the quiet sun. So the more a feature deviates from the quiet sun, the stronger its contribution to the RV signal. Each point on the plot represents the mean velocity within a mu bin, and the shaded regions show the distributions. Here we can see that mote flows have a distinct center to limb trend from the other features. The trends of motes are similar to those of plage and network, but with a higher dispersion due to the nature of the feature itself. There's a wider range of velocities occurring in mote flows compared to the other features. These plots show the probability density of the total velocity and suppression of convective blue shift for individual mu bins. So we can see the shapes of the distributions shaded in the previous figure. We can see that the mote flows are similar to both plage and penumbra. Like plage, the distribution of velocities is greater at the limb, where we are observing horizontal motion, than at disk center, where we are observing vertical motion. The distributions are also of similar shape and position to penumbra, but of higher density. This makes sense because mote flows have a similar intensity and magnetic field strength to plage, but are slower and flow more horizontally outside penumbra. A next step is to scale the distributions of plage and penumbra to try to match mote flows and compare the shapes directly. To adjust the RV curves of similar location and spot sizes having different amplitudes in previous plots, I also plotted mote flows left and right of the center meridian separately to see if there was a difference. For solar physicists, left is east and right is west. However, it turns out that there was no strong difference between the two. And this is the same plot as before, but with left and right separated. So in this project, we quantified the RV signal of mote flows. Going back to the beginning, the blue line shows a time series of the suppression of convective blue shift of the entire sun, and the green line shows the suppression of convective blue shift for mote flows. And comparing the two, it makes it clear that mote flows play a noticeable role in the overall RV signal, giving us a better understanding of how these flows contribute to the stellar noise that masks exoplanets. We can apply this knowledge to models of the sun to better correct for stellar noise in RV measurements and find more exoplanets. So, in conclusion, the radius of a mote flow is proportional to the size of its sunspot, but in complex regions of sunspot, motes generally have smaller radii. The center to limb variability trends of motes are similar to those of plage and penumbra, but with a higher dispersion. Mote flows have a wider, this is because mote flows have a wider variety of velocities in the horizontal direction than the vertical direction. Since we have quantified RV signals from mote flows, we can account for their noise in stellar RV models, bringing us closer to detecting smaller, potentially habitable exoplanets. And there are still noise sources out there to account for in the future. Thank you.
Excellent, Savannah. Questions? Sam.
Very nice talk. Could you go back to the the final results one where you compared both your, yeah, the feature on the right that jumps out to me the most in your results, around 5, 6, 800, looks like it's lined up really well with a very small peak in like the total RV of the entire sun. Is there any possibility they're connected?
So, are you talking about
Around
peaks down here matching
Yeah.
up here? Yes, those are related. So, what we're trying to do is take away or account for this noise in this signal so that we can detect the signals of smaller exoplanets whose like velocity wobbles are smaller.
Any other questions? Torsren.
Thank you, Savannah. Would it make sense in that case to subtract the green data from the blue data, and that's what you would expect to find planets in other stars? Am I understanding that right? Like, so subtract the green as like a background.
Yeah. Yes, we're trying to subtract noise sources.
Yeah, okay.
Yeah.
Cool.
More questions? Julio.
Nice talk. Have you looked at, then the sun is very quiet, so no sunspots, nothing. Because that was, I was thinking, you know, obviously stars like the sun have cycles. If you pick, looking maybe at the wavelengths, stars when they are in a quiet phase, then you reduce all these problems. But, you know, that's why I was asking if you looked at the, because you mentioned quiet sun, but I think you picked regions of your data in 2000 and you said 14, 15, whatever, of sort of quiet sun, but that wasn't solar minimum, you know. If you have to look at solar minimum to really see the quiet sun.
Yeah. So you're right. So I looked at data in 2014 where there were a lot of sunspots and a lot of sunspot motes. But when we are going to apply this knowledge to other stars, we would consider, I think we would consider if they had a cycle and how much of the surface would be mote flows, and like change that constant for mote flows that we are applying. Yeah.
Any other questions? Going once? Going twice? All right, I'll ask the question. What was the most fulfilling part of your research?
That's a good question. Well, an interesting part of my research is that I am modifying code that already exists, and so it was really cool to see at the end, like with these plots, how the signatures that we were seeing from different features on the sun matched with that, and how they were different, and like how mote flows are now taken into account, and like the reclassification of the pixels. So I'm excited to see like how when we account for more different features, like how that affects the RV signal.
So it sounds like you liked the whole thing. All right, and that's all the time we have for questions. So let's give Savannah another round of applause. presenter notes or anything?
Nope.
All right. Our last talk of the day will come from Leah Shipley. So she is going to discuss when eruptions simply don't erupt. So Savannah received her associates recently from Front Range Community College, and she's transferring to Metro State University in Denver to research, I believe, a bachelor's in meteorology?
That's
Correct.
right.
Excellent. And whenever you're ready, take it away, Leah.
Thank you. My name is Leah, and I will be talking about solar flares, and specifically those that fail to erupt, and they don't contribute to aurora such as in this photo. So all solar flares originate from active regions on the sun and emit radiation. In addition to radiation, powerful solar flares usually release plasma and magnetic field lines into space. These are known as coronal mass ejections. Such flares are known as eruptive flares. When Earth-directed, these CMEs cause geomagnetic activity, and that's what contributes to aurora, to satellite disturbances, and potentially even electrical grid disturbances. However, some flares fail to erupt and are not associated with CMEs, even though they were radiative. These flares are referred to as confined flares. Understanding the characteristics of confined solar flares may help us additionally understand eruptive flares. Previous studies of flares have indicated that confined flares tend to originate from the center of large active regions, while eruptive flares can originate from a small active region or the edge of a large active region. So this is the basic structure of a flare. Active regions, they will have at least two magnetic polarities, and when flares occur, a pair of polarities will also have corresponding footprints on the surface of the sun, as well as ribbons that connect those loops that connect those ribbons. The bright top of a loop is where the flare originates. So we can see the ribbons in the AIA 304 and 1600 wavelengths, and the loops are best visible in AIA 94, 131, and 193. So I looked at a specific active region that occurred last year in February. So it was known as 13590, and this active region was interesting because it produced quite a few very powerful flares, including 3 X-class flares. One of them peaked at 6.4. So you can see in this plot here, that shows the location of each flare. So you've got the 3 X-class flares at the beginning, and then there's a lot of M-class flares as well. And we will see later that the blue one all the way at the right, also known as the western part of the sun, that is one that did erupt. All the other ones, they were confined. So for this project, I plotted the GOES soft X-ray flux, and I also plotted the SDO, AIA, and HMI data for the most notable flares, and analyzed their magnetic fields and structures by plotting and stacking contour lines. So all of these flares, they occurred within a period of 7 days, and this is the GOES X-ray plot. So the sun symbol there that is yellow, that is the flare that successfully erupted, and then there were quite a few M-class flares that occurred earlier in that week, and each of those sun markers that are not yellow, those are all flares that were stronger than the eruptive flare, but they all remain confined. These are the GOES signatures, so they are the GOES plots. Each one is a period of 6 hours, with the peak of the flare approximately in the middle there. And you can see in the first one so the peak there is of the X6.4 flare. And it only lasted about a couple of hours. And before that, you can see an additional M-class flare that was also confined. In the second plot, that is the M-class flare that did successfully erupt. And it had a much longer duration. It lasted several hours. So active region 13590 had a very complex magnetic field. And the basic structure of a flare that we saw earlier, that only had 2 magnetic polarities. This active region had at least 4 main magnetic polarities,
And later we will watch a video that shows how it changed over the course of these several days. And also take note, so I have the main magnetic polarities numbered, and the third one, that negative polarity, that is where both the X6.4 flare and the M1.3 eruptive flare originated from. So there is the active region crossing the sun, and you can see those main polarities there, and it's quite a large active region. And you can see that once it crosses the center of the sun, it changed quite a bit by the time it got towards the limb of the sun. So let's take a closer look at the confined X6.4 flare. So like I said, we can see the flare ribbons pretty well in the 304 and 1600 wavelengths. So this is right at the start of the flare. And this is also an AIA. This shows the loops at the start of the flare, connecting those ribbons. Once we get to the peak a few moments later, you can see that the flare ribbons have brightened quite a bit, especially those two right there. And then here are those loops connecting them. And there's some diffraction there, even though this is such a short exposure. This was a very, very bright flare. So I took contours from the AIA images. So here you can see the orange and the red. Those are the very brightest points on the AIA 304, which shows the ribbons. And then the blue is the loops. So you can see that there's some structure developing here at the start of the flare. And once we get to the peak, it so happens that the brightest ribbon and the bright loop top happen to be approximately in the same spot there. That's where you see the darker blue and the red. And this is plotted on top of the magnetogram, so you can see that this is pretty much in the center of the active region, which is what we expect, since previous studies have indicated that a confined flare will originate from the center of a large active region. Now we get to the eruptive M1.3 flare. So again, these are the ribbons beginning to brighten. And here are some loops. Now these AIA images are from near the beginning of the peak, and you can see that one of the ribbons there is quite bright. And this is my favorite AIA image that I generated over the summer. I think it's really spectacular seeing that flare brightening there. And unfortunately, this flare was closer to the limb of the sun, so we're looking at this from an angle, so we can't see it like all the detail as well as we would like to, but it's pretty neat. And then here are those contours highlighting the ribbons and the loops beginning to develop. And this is right before the peak of the flare. And again, you can see that really bright ribbon there. And then off to the side is the bright loop top. And one thing that I did is which I'll show you later where the flare originated from. I used the Stony-Hurst latitude and longitude to approximate where it originated on the magnetogram. So here are those images. So the first one is from the X6.4 flare. So you can see the yellow dot shows where it originated from. And it's pretty easy to determine that because we're looking at it almost directly straight, since this flare was close to the center of the sun at that time. But once we get to the eruptive M1.3 flare, it's rotated pretty close to the limb. So the green dot showing the origination of that flare is a little bit more difficult to determine, but it still appears to be fairly close to the center of this active region, near that negative polarity. So in conclusion, previous studies, again, they indicated that confined flares erupt from near the center of large active regions, while eruptive flares can originate from a small active region or the edge of a large region. we find that all of this active region's strong flares, including the eruptive one, emerge close to the center of this large active region, which may suggest that there is more to the confinement of powerful flares than the location of their origin within an active region. Visual analysis of the magnetogram and flare structure suggests that the magnetic field at the point of the flare origin may have been stronger during earlier confined flares, then weakened by the time the eruptive flare occurred. We noted the complexity of active region 13590 with multiple magnetic polarities. The X6.4 and M1.3 flares were more detailed than the standard model, with multiple sets of flare ribbons and loops each. So for future work, potentially this study could benefit from magnetic field modeling of this active region. And I will continue to study Solar Cycle 25's active regions, as it has produced a diverse array of solar flares. We will continue to analyze SDO, HMI, and AIA data for other powerful flares, comparing the differences in magnetic fields and flare structures between confined and eruptive flares, as well as the active regions that they originate from. Here are my references, and I am deeply grateful to my mentors, Dr. Ting Go and Dr. Catherine Reeves, for their patient guidance and sharing all of their knowledge with me this summer. And I'm very grateful as well to Dr. Chad Madsen for directing this solar program, and also to Dr. Xiaoyan Xie for her guidance with technical difficulties earlier, and for the NSF funding this program. So thank you all.
Fantastic. Thank you, Leah. Questions? All right.
Hi, Leah. Amazing talk. And I just had a question about what is the difference between the flares that erupt and the flares that don't erupt?
Yes. So what all flares have in common is they all emit radiation, and they all originate from active regions. So the differences are that, and I can go back to the structure of a flare. So they all have like the loops and the flare ribbons in common as well. The only thing that's different between a confined flare and an eruptive flare is that a confined flare does not release a coronal mass ejection, which is plasma and magnetic field lines into space. So that's the goal, is to figure out why some do and some don't.
Thank you.
Of course.
More questions? Torsren.
Thank you, Leah. Can you point out where the flare ribbons are on one of the pictures that you took? I don't know if I noticed one.
Sure.
I don't know if I was looking, but.
So it's pretty hard to see at the beginning of the flare. They're easiest to see at the peak of the flare. So you can see 4 main ribbons here, and 2 of them are especially bright. Let's see if, yeah, so here's the brightest one right here, and then this is also pretty bright, and then we've got one here and here. And then when you look at the contours, those would be the orange regions here. And the very brightest point is the red there, but yeah, so those are for the X6.4 flare. And then going to the M1.3, again, this is pretty close to the peak. So there's this one that's like kind of an interesting shape there, and little ones off to the side here. And then when you look at the AIA itself, like that's the very bright ribbon here, and then there's a ribbon here.
Okay, I think I see it. Thank you.
Sure.
Any more questions? All right.
So I guess like similar to like Toast's question, I have a question again about the eruptive flares versus the non-eruptive flares though. So is there like like any one of these plots that has like I guess a photograph of eruptive flares and how that looks like compared to one that's not erupted?
Yeah, so basically a flare is like a burst of radiation, right? So this is the eruptive flare, and like someone can fact check me if I say something incorrect, but so with this eruptive flare, these loops that you see here are what's going to be released as a coronal mass ejection. Is that correct? Or those are below? Okay. Right, so we can't really tell visually then whether it's going to erupt. So yeah, this is just what a flare looks like closer to the limb of the sun, and then once we go back to this confined one, like this is the confined flare, but just from looking at this, I don't think we can really tell whether it's going to be confined or eruptive. Like, we have to wait until later when we look at the coronagraph to see whether there was an eruption for it.
Can you say a little bit about the differences in the GOES curves between the confined and the eruptive?
Yes, so the GOES curves. So going back to where we have all of these flares together, so notice that the confined flares earlier in the week, they're very impulsive. So they quickly rise and they quickly fall. Once we get to this eruptive flare, it's much longer duration, so it rises and then it remains for quite a bit longer. And then comparing, so the first one is the confined flare, and then the second one is an eruptive flare. And again, you can see with the confined flare, so the radiation level quickly rises and then it fairly quickly subsides. Whereas with the eruptive flare, it rose and just remained for quite some time.
Chriselle?
I have a quick question. Do you look at the precursor of the flare and see if there's any geometric configuration that you saw that maybe in the so in solar flares there's the hot onsets that are before the flare that show a small temperature increase. So I was wondering in your analysis if you saw some configuration in the topology or in the ribbons that might show that they're being shifted or configured before the actual flare. So in your images under HMI or AA, if there was some morphology changes that that might be surprising for you that could have triggered the event.
That is not something that I've noticed. If either of my mentors have any further comment on that.
Yeah, that's a really good question, and it's something we didn't really address in this project. Just a little background for people that don't know. There's been some work recently that has shown that there's a temperature increase kind of prior to the flare as a precursor. And this is something I've actually wanted to look for in XRT, actually, not the data that Leiyla is using. To see if we can figure out what a visual indicator of that hot precursor is. But yeah, that's a really good question. It's something I'm interested in, but we didn't really address it with this project.
Thank you for that question.
All right. Robert.
Hi, thank you for the talk. I really enjoyed it. I had another question about GOES. Did you look at just the it seems like you just have a lot of the raw flux data. Did you look at any other characteristics of these flares, like temperature, emission measure, the energy release rate of these flares, or?
No, I just looked at the GOES raw data and then, of course, the SDO HMI-AA data.
Thank you.
Anybody else? I might ask one if nobody else has one. So, this active region, this is something similar to I asked you earlier in the year, but it's a question that has haunted me. So, the magnetic configuration of this active region is super weird. So, is all I'm going to have to say. So, when you have a fully emerged active region, you should expect a dipole with some parasitic flux mixed in there. This is a full quadrupole. So you've selected quite possibly one of the weirdest active regions I've ever seen. So have you been able to maybe identify what this particular configuration, whether that contributed to any of the confinement?
Well, I would expect the size of it and also the strength of it to contribute, especially, to the confinement, especially earlier on. You might notice that, so these negative regions highlighted with the blue contours, it's kind of diffuse, and that may be left over from a previous active region that's decayed a little bit, but it still has enough strength here. And then it seems like these two would be stronger. Now, if we go back to the video, you can see how that changes, especially once it hits the center of the disk. There's quite a bit. So the left side of it seems to be decaying.
It almost looks like this area here and this area which you labeled, I think, number 2, is almost like some overlying plage from like a previous region. So, but it's causing all sorts of madness. So.
Yeah, and then, so looking back at like the points of origin, so we have the eruptive one coming from here, and when we look close to the peak, so you have the brightest ribbon here, which it's interesting that it's in this part of the magnetic field that seems to have decayed, right? Mm-hmm. But then perhaps it's kind of hard to tell, but like there's ribbons out here, and it seems like there's a really bright loop connecting these parts. So perhaps the fact that this part of the magnetic field has decayed so much, that contributed to this flare being able to erupt. Even though it's still quite large, it's weakened.
Yeah, I would expect still to be a pretty significant kind of overlying canopy of magnetic field that is probably going from one network region to the other. So I would expect it to be more confining, but of course, I guess it's based on whatever the orientation of the erupting flux is. So this is a really cool active region.
Yeah, there was definitely a lot that happened because, as we can see, like a bunch of flares happened here in this time period. Then there was nothing for a while, so the magnetic field was probably changing, and then by the time we got to this flare that did erupt, it was able to erupt rather than remain confined.
Yeah. Could have had some multiple eruption phases. Interesting. All right. Thank you, Leah.
Thank you.
All right. With that, so I have a couple of announcements and then some final words before we part. So, first announcement is that for the solar students, after this, we are going to meet in the courtyard for group photos. So, be prepared for that. So, at 3:30, the Du Bois scholars are going to give their talks. So please come to their talks and support them. So, and congratulate them on their work. So that'll be right back here in Phillips. And some final words. I'm going to level with you. Science is really hard. So, and the fact that an undergrad could produce this level of novel research in 10 weeks is impressive. And I want you all to know that I'm very proud of you, and you should be very proud of yourselves, every single one of you. So this is not a normal level of achievement. So, in 10 weeks. So, I want everybody to give our students a round of applause, because they definitely. On top of that, so a big part of their success was the close and quality mentorship that they received from staff from the SSXG, as well as actually some external staff too. So I want you to give them a hand too. So. So these mentors literally volunteer their time. So the NSF grant does not allow us to pay them. So, these people took their time out to ensure that the next generation of scholars, are brought up with the research skills they need. So, with that, I declare this a successful REU program. You nailed it.